Chapter 24. G. Marconi's method, even the lightning elf who rides the oak and barbs the tempest, shall bow to that yoke, and be its messenger to run. Supple's dampier his dream. We now come to the crowning work of Mr. Marconi in wireless telegraphy, but before describing this method, it will be desirable to make ourselves acquainted with the principles involved in the special apparatus which he employs, and which differentiates his system from all those that have hitherto occupied us. For this we need only go back a few years and make a rapid survey of the epoch-marking discoveries of a young German philosopher, Heinrich Hertz. To properly appreciate the work of Hertz, we must carry our minds back 200 years to the time when Newton made known to the world the law of universal gravitation. Here, in the struggle between just-Newtonianism and the dying Cartesian doctrine, we have the battle royal between the rival theories of action at a distance and action by contact. The victory was to the former for a time, and in the hands exceedingly sensitive that they will respond to the very minute traces of current picked up by the broken end on the receiving side, from that which is spreading out through the water in all directions from the broken end on the sending side. See Mr. Brown's patent specification number 3123 of December 31st, 1896. Recently, he has been successful in bridging over in this way a gap in one of the Atlantic cables. But in this, he has done nothing more than the present writer did in 1881, and Mr. Willoughby Smith in 1887. Of Bernoulli, and subsequently of Boscovich, the doctrines of Newtonianism were carried far beyond the doctrines of the individual Newton. In fact, Newton expressed himself as being opposed to the notion of matter acting where it is not, though, as we see by his support of the emission theory of light, he was not prepared to accept the notion of a luminiferous ether. Newton, however, suggested that gravitation might be explained as being due to a diminution of pressure in a fluid filling space. Thus, the doctrine of an empty space, requiring the infinitely rapid propagation of a distance action, held the field, and was recognized by scientists of the 18th century as the only plausible hypothesis. History repeats itself, and again the battle royal was fought, this time early in the 19th century, in favor of the ether hypothesis, and action at a distance was mortally wounded. Before the phenomena of interference of light and the magnetic and electrostatic researches of Faraday, both the idea of empty space action and that of the emission of light failed, and the propagation of force through the ether and of light by vibratory conditions of the ether came to be held as necessary doctrines. Later still, one Maxwell assumed the existence of and investigated the state of stress in a medium through which electromagnetic action is propagated. The mathematical theory which he deduced gives a set of equations which are identical in form with the equations of motion of an infinite elastic solid. And on this theory, the rate of propagation of a disturbance is equal to the ratio of the electromagnetic and electrostatic units. The experimental determination by Maxwell and others that this ratio is a number equal to the velocity of light in ether in centimeters per second is a fact which gave immense strength to the Maxwellian hypothesis of identity of the light and electromagnetic. But although this is the case, the Maxwellian hypothesis, even when taken in conjunction with the experimental support which he edges for it, fell far short of being a complete demonstration of the identity of luminous and electromagnetic propagation. To the genius of Hertz, we owe this demonstration. One of the most important consequences of Maxwell's theory was that disturbances of electrical equilibrium produced at any place must be propagated as waves through space, with a velocity equal to that of light. If this propagation was to be traced through the small space inside a laboratory, the disturbances must be rapid, and if a definite effect was to be observed, they must follow each other at regular intervals. In other words, periodical disturbances or oscillations of extreme rapidity must be set up, so that the corresponding wavelength, taking into account the extraordinarily high velocity of propagation, 186 miles per second, maybe only a few inches or at most feet, Hertz was led to an experiment which satisfied these conditions and thus supplied the experimental proof which Maxwell and his school knew must come sooner or later. The oscillatory nature of the discharge of a Leyden jar under certain conditions, was theoretically deduced by von Helmholtz in 1847. Its mathematical demonstration was given by Lord Kelvin in 1853. And it was experimentally verified by Feddersen in 1859. When a Leyden jar or a condenser of an inductive capacity K is discharged through a circuit of resistance K and self-induction L, the result is an instantaneous flow, or a series of oscillations according as R is greater or less than 2 equals. And in the latter case, the oscillatory period or amplitude is given in the equation, where Tt is the constant 3 to 1415 Phil. Trans, June 1853. In his collected papers, Hertz tells us that his interest in the study of electrical oscillations was originally awakened by the announcement of the Berlin Prize of 1879, which was to be awarded for an experimental proof of a relation between electrodynamic forces and dielectric polarization in insulators. At the suggestion of his master and friend, von Helmholtz, the young philosopher took up the inquiry, but soon discovered that the then known oscillations were too slow to offer any promise of success, and he gave up the immediate research. But from that time, he was always on the lookout for phenomena in any way connected with the subject. Consequently, he immediately recognized the importance of a casual observation, which in itself and at another time might have been considered as too trivial for further notice. In the collection of physical apparatus at Karlsruhe, he found an old pair of so-called Ries's or Nackenhauer's spirals, short flat coils of insulated wire with the turns all in the same plane, Ipria-Fenry spirals. While performing some experiments with them at a lecture he was giving, he noticed that the discharge of a very small Leyden jar, or of a small induction coil, passed through the one was able to excite induced currents in the other, provided that a small spark gap was made in the circuit of the first spiral. Thus was made the all-important discovery of the effective spark gap which started Hertz on the road of his marvelous investigations. A very little consideration of this phenomenon enabled him, even at this early stage, to lay down the following propositions. 1. If we allow a condenser, such as a Leyden jar, of small capacity, to discharge through a short and simple circuit with a spark gap of suitable length, we obtain a sharply dense discharge of very short duration, which is the long sought for sudden disturbance of electrical equilibrium, the exciter of electrical vibrations, 2. Such vibrations are capable of exciting in another circuit of like form resonance effects of such intensity as to be evident even when the two circuits are separated by considerable distances. In this second circuit, Hertz had found the long sought-for detector of electric waves, with the exciter to originate electric waves and the detector to make them evident at a distance. All the phenomena of light were one after another, reproduced in corresponding electromagnetic effects, and the identity of light and electricity was completely demonstrated. In his paper on very eepid electric oscillations, Hertz occupied himself with some of these phenomena. As an exciter, he used wire rectangles or simple rods, the figure, to the ends of which metallic cylinders or spheres were connected, the continuity being broken in the middle where the ends were provided with small spherical knobs between which the sparks passed. The exciter was charged by an ordinary Uhm-Korf induction coil of small size. The detector was mostly a simple rectangle or circle of wire, the figure, also provided with a spark gap. When vibrations are set up in the detector and sparks pass across the gap, the greater length of these sparks indicates the greater intensity of the received wave impacts. When, therefore, the dimensions of the detector are so adjusted as to give the maximum sparks with a given exciter, the two circuits are said to be in resonance or to be electrically tuned. In the course of his experiments on electric resonance, Hertz observed a phenomenon which, for a time, was inexplicable. It was seen that the length and brightness of the sparks at the detector were greatly modified by the sparks given off at the exciter. If the latter were visible from the detector spark gap, the sparks given off there were small and hardly perceptible, but became larger and brighter as soon as the screen was placed between the two instruments. By carefully thought-out experiments, he showed that this singular action was due solely to the presence of ultraviolet light thus furnishing a proof of the connection between light and electricity. Having made himself familiar with the phenomena of electrical resonance, Hertz went on to study the propagation of electric vibrations through space, the most difficult as it is probably the most important of all his researches. The results he gave to the world in 1888 in his paper on the action of a rectilinear electric oscillation on a neighboring circuit, when sparks pass rapidly at the exciter, electric surgings occur, and we have a rectilinear oscillation which radiates out into surrounding space. The detectors, whose spark gaps were adjustable by means of a micrometer screw, were brought into all kinds of positions with respect to the exciter, and the effects were studied and measured. These effects were very different at different points and in the different positions of the detector. In short, they were found to obey a law of radiation, which was none other than the corresponding law in optics. In his paper on the velocity of propagation of electrodynamic actions, he gave experimental proof of the hitherto theoretical fact that the velocity of electric waves in air was the same as that of light, whereas the velocity in wires was found to be much smaller in the ratio of 4:7. For the moment he was puzzled by this result. He suspected an error in the calculations or in the conditions of the experiment. But, and here he showed himself the true philosopher, he did not hesitate to publish the actual results, trusting to the future to correct or explain the discrepancy. The explanation was soon forthcoming. Messrs. E. Saracen and L. de la Rive of Geneva took up the puzzle and ended by showing that the deviations from theory were caused simply by the walls of Hertz's laboratory, which reflected the electric waves impinging on them, so causing interferences in the observations. When these investigators repeated the Hertzian experiment with larger apparatus and on a larger scale, as they were able to do in the large turbine hall of the Geneva waterworks, they found the rate of propagation to be the same along wires as in air. In his paper on electrodynamic waves and their reflection, Hertz further developed this point and showed the existence of these waves in free space. Opposite the exciter, a large screen of zinc plate, 8 feet square, was suspended on the wall. The electric waves emitted from the exciter were reflected from the plate, and on meeting the direct waves interference phenomena were produced, consisting of stationary waves with nodes and loops. When, therefore, Hertz moved the circle of wire which served as a detector to and fro between the screen and the exciter, the sparks in the detector circuit disappeared at certain points, reappeared at other points, disappeared again, and so on. Thus there was found a periodically alternating effect corresponding to nodes and loops of electric radiation, showing clearly that in this case also the radiation was of an undulatory character, and the velocity of its propagation finite. In a paper on the propagation of electric waves along wires, March 1889, Hertz shows that alternating currents or oscillations of very high frequencies, as 100 million per second, are confined to the surface of the conductor along which they are propagated and do not penetrate the mass. This is a very important experimental proof of Poynting's theory concerning electric currents, which he had deduced from the work of Faraday and Maxwell. According to this theory, the electric force, which we call the current, is in no wise produced in the wire, but under all circumstances enters from without and spreads itself in the metal comparatively slowly, and, according to similar laws, as govern changes of temperature in a conductor of heat. If the electric force outside the wire is very rapidly altering in direction or oscillating, the effect will only enter to a small depth in the wire. The slower the alterations occur, the deeper well the effect penetrate, until finally, when the changes follow one another infinitely slowly, the electric effect occupies the whole mass of the wire with uniform density, giving us the phenomenon of the so-called current. Reviewing his experiments on this subject, Hertz says a difference will be noticed between the views here put forward and the usual theory. According to the latter, conductors are represented as those bodies which alone take part in the propagation of electric disturbances. Non-conductors are the bodies which oppose this propagation. According to our view, on the contrary, all transmission of electrical disturbances is brought about by non-conductors. Conductors oppose a great resistance to any rapid changes in this transmission. One might almost be inclined to maintain that conductors and non-conductors should, on this theory, have their names interchanged. However, such a paradox only arises because one does not specify the kind of conduction or non-conduction considered. Undoubtedly, metals are non-conductors of electric force, and just for this reason, they compel it under certain circumstances to remain concentrated instead of becoming dissipated. And thus they become conductors of the apparent source of these forces, electricity, to which the usual terminology has reference. In the course of his experiments, Hertz had succeeded in producing very short electric waves of 30 centimeters in length, the oscillations corresponding to which could be collected by a concave cylindrical mirror and concentrated into a single beam of electric radiation. According to Maxwell's theory of light, such a beam must behave like a beam of light. And that this is the case, Hertz abundantly proved in his next paper on electric radiation. He showed how such radiation was propagated in straight lines like light, that it could not pass through metals, but was reflected by them, that, on the other hand, it was able to penetrate wooden doors and stone walls. He also proved by setting up metallic screens that a space existed behind them in which no electric action could be detected, thus producing electric shadows, and by passing the electric rays through a wire grating, he was able to polarize them, just as light is polarized by passage through a nickel prism. Perhaps the most striking experiment of all in this field was his last one, in which he directed the ray onto a large pitch prism weighing 12 cws. The ray was deflected, being in fact refracted like a ray of light in a glass prism. Thus, he gave to the experimental demonstration of Maxwell's electromagnetic theory of light its finishing touch, and the edifice was now complete. Hertz's marvelous researches were presented in succession, as rapid and surprising almost as the sparks with which he dealt to the Berlin Academy of Sciences between November 10, 1887, and December 13, 1889. They were collected and published in book form in 1893 under the title of Electric Waves, English translation, edited by Professor D.E. Jones, to which the reader is referred for further information. Here, it will suffice, in conclusion, to briefly sum up the chief results of these epoch-making investigations. In the first place, Hertz has freed us from the bondage of the old theory of action at a distance, and, as regards electric and magnetic effects, he has shown that they are propagated through the ether, which fills all space with finite velocity. The mysterious darkness which surrounded those strange distance actions, that something can act where it is not, has now been cleared away. Further, the identity of the form of energy in the case of two powerful agents in nature has been conclusively established. Light and electrical radiation are essentially the same, different manifestations of the same processes. And so the old elastic solid theory of optics is resolved into an electromagnetic theory. The velocity of propagation of light is the same as that of electromagnetic waves, and these in turn obey all the laws of optics. The scope of optics is thus enormously widened. To the ultraviolet, visible, and infrared rays, with their wavelengths of thousandths of a millimeter, are now to be added, lower down the scale, electromagnetic waves, producible in any length from fractions of an inch to thousands of miles. Hertz's ordinary waves were many meters long, and he does not appear to have ever worked with waves of less than 30 centimeters. Righi, however, by employing exciters with small spheres, obtained waves of 2 centimeters, while Professor Chandrabose of Calcutta, using little pellets of platinum, was able to produce them of only 6 millimeters. The smaller the pellets, the shorter the electric waves, until we come in imagination to the pellet of the ultimate atom, whose waves should closely approximate to light. The following table compares approximately some of the known vibrations in ether and air. Ether vibrations per second, billions, equals Röntgen rays. 10-0 equals actinic, 8-0, it equals violet, 5-500, M equals green, 40U equals red, 288 and equals infrared 10 to 2, 0 equals radiant heat, 50 thousands to 20 billions equals Hertzian waves, air vibrations per second, 33, 0 equals highest audible note, 40 equals highest musical note, 20 equals highest soprano. 150 to 500 equals ordinary voice. 32 equals lowest musical note. 16 equals inaudible U in another direction. We owe much to Hertz's investigations. We are brought nearer to a solution of the question, what is electricity? One, he shows us that it is not an entity of the nature of a fluid, as in the older theories. What we wish to explain by assuming electricity is in reality nothing but a condition of a medium, which, although hypothetical, manifests itself by its effects, namely the ether which fills all space and permeates all matter. The work of Hertz was immediately taken up and is now being carried on, doubtless towards fresh conquest. For there is no finality in science, by a whole army of investigators, of whom we need only mention a few, as Lodge, Iggy, Branly, Saracen, and de la Rive, whose discovery is especially as regards the exciter and detector. More immediately concern us in this history, the exciter of Hertz, although sufficing for his special purposes, had the disadvantage that the sparks in a short time oxidized the little knobs and roughened their surfaces, which made their action irregular and necessitated their frequent polishing. Messrs. Saracen and de la Rive of Geneva obviated this difficulty by placing the knobs in a vessel containing olive oil. The effect of this arrangement was at once to augment the sparks at the detector, so that when it was placed close to the exciter, the sparks were a perfect blaze, and at 10 meters distance, with detectors of large diameter 75 to 1 meter, they were still very bright and visible from afar. It is true that here too the oil carbonizes in time and loses its transparency. But if a considerable quantity, as 2 or 3 liters, be employed, there is no perceptible heating, and the intensity of the sparks is hardly altered, even after half an hour's continuous working. Professor Righi substituted Vaseline oil, made suitably thick by the addition of solid Vaseline. His exciter is composed of 2 metal balls, each set in an ebonite frame. A parchment envelope connects these frames and contains the oil, which thus fills the spark gap. Righi attributes the increased efficiency of his exciter, one, to the heightening effect which a cushion of liquid seems to have on the electric potential which gives rise to the sparks, a sort of, to adopt an expressive French phrase, reculant or mieux sauter, and to some sort of regularizing effect, making their production more uniform. Like Saracen and de la Rive, he found that the use of Vaseline obviated the necessity of frequent cleaning of the knobs, for even after long usage. When the liquid had become black and a deposit of carbon had formed on the opposing surfaces, the apparatus continued to work satisfactorily. Iggy also found that solid knobs gave better results than hollow ones, the oscillations in the former case being perceptible in the detector at nearly double the distance attained in the latter case. The detector usually employed by Hertz consisted of a metal wire bent into a rectangle or a circle and terminated by 2 little knobs between which the sparks played. But this form is not obligatory. Any 2 distinct conducting surfaces separated by a spark gap will serve equally well. Many kinds of detectors have been employed, but in this place we need only concern ourselves with those of the microphonic order, which alone enter into the construction of the Marconi system of telegraphy. Just mentioning the well-known electrical behavior of selenium under the action of light, the fact observed by Professor Minchin that his delicate impulsion cells were affected by Hertzian waves, the Righi detector, consisting of thin bands of quicksilver, as used for mirrors, rendered discontinuous by cross lines lightly traced with a diamond, and the original Lodge coherer consisting of a metallic point lightly resting on a metal plate too, we come to the special form known as Branly's detector, or, as he prefers to call it, the radioconductor. The observance of the phenomenon manifested in Branly's detector goes back much further than is usually supposed. Mr. S.A. Marley was, I believe, the first to notice it, and as long ago as 1866 he applied it in the construction of a lightning protector for telegraph apparatus. In his paper read before the British Association, Liverpool meeting, 1870, he says, the author, when experimenting with electric currents of varying degrees of tension, had observed the very great resistance which a loose mass of dust composed even of conducting matter will oppose to electric currents of moderate tension. With a tension of, say, 50 Daniell cells, no appreciable quantity will pass across the dust of black lead or fine charcoal powder loosely arranged, even when the battery poles are approached very near to one another. If the tension be increased to, say, 200 or 300 cells, the particles arrange themselves by electrical attraction close to one another, making good electrical contact, and forming a channel or bridge through which the electric current freely passes. When the tension was still further increased to 600 or 700 cells, the author found the electricity would pass from one pole to the other through a considerable interval of the ordinary dust which we get in our rooms, and which is chiefly composed of minute particles of silica and aluminum mixed with more or less carbonaceous and earthy matters. Incandescent matter offers a very free passage to electrical discharge, as is indicated by the following experiments. The author placed masses of powdered black lead and powdered wood charcoal in two small crucibles. No current would pass through these masses whilst they were cold, however close the poles were approached without actually touching. The battery employed in this experiment was only 12 cells. The crucibles were then heated to a red heat, and electricity freely passed through the heated powder, and testing the resistance opposed by the heated particles Placing the poles 1 inch apart and employing only 6 cells, the average resistance opposed by the black lead was only 4 British Association units, and that opposed by the wood charcoal 5 units. The average resistance of a needle telegraph coil may be taken at 300 units, or ohms, as they are now termed. These observations go to show that an interval of dust separating two metallic conductors opposes practically a decreasing resistance to an increasing electrical tension, and that incandescent particles of carbon oppose about GZF, part of the resistance opposed by a needle telegraph coil. Easing upon these data, the author was led to construct what he terms a lightning bridge, which he constructs in the following way. 2 thick metal conductors terminating in points are inserted usually in a piece of wood. These points approach one another within about all feet of an inch in a chamber cut in the middle of the wood. This bridge is placed in the electric circuit in the most direct course which the lightning can take, as shown in the diagram, the figure, and the space separating the 2 points 33 is filled loosely with powder, which is placed in the chamber and surrounds and covers the extremities of the pointed conductors. The powder employed consists of carbon, a conductor, and a non-conducting substance in a minute state of division. The lightning finds in its direct path a bridge of powder, consisting of particles of conducting matter in close proximity to one another. It connects these under the influence of the discharge and throws the particles into a highly incandescent state. Incandescent matter, as has been already demonstrated, offers a very free passage to electricity. And so the lightning discharge finds an easier passage across the heated matter than through the coils. The reason a powder consisting entirely or chiefly of conducting matter cannot be safely employed is that, although in the ordinary conditions of things it would be found to oppose a practically infinite resistance to the passage of electricity of the tension of ordinary working currents, when a high-tension discharge occurs, the particles under the influence of the discharge will generally be found to arrange themselves so closely as to make a conducting connection between the 2 points of the lightning bridge. This can be experimentally demonstrated by allowing the secondary currents developed by a Ruhmkorff's coil to spark through a loose mass of black lead. The crucial test, however, is the behavior of the bridge in practice. These lightning bridges have been in use since January 1866. At the present time, there are upwards of 1,000 doing duty in this country alone, and not a single case has occurred of a coil being fused when protected by them. It is only right, however, to mention that 3 cases, but 3 cases only, have occurred where connection was made under the influence of electrical discharge between the 2 metallic points in the bridge. The protectors in which this occurred were amongst those first constructed, in which a larger proportion of conducting matter was employed than the inventor now adopts. The points also in those first constructed were approached to 0.1 of an inch from one another, and the author has no doubt from an examination of the bridges afterwards that under the influence of a high-tension discharge connection was made between the two metallic points by a bridge of conducting matter arranged closely together. And if the instruments had been shaken to loosen the powder, all would have been put right. In one of these three cases, and it was the only one in which the author was supplied with the details, he ascertained that the protector was attached to a needle telegraph. Having the ordinary magnetic needles made of tempered steel magnetized, and on the removal of the bridge after the discharge, so completely had the electricity been carried away by the bridge, that the magnetism of the magnetic needle was found not to have been affected. In the little-known researches of the Italian professor Calzecchi-Wensti, we find this curious phenomenon again cropping up. In 1884 to 85, Professor Calzecchi-Wensti found that copper filings heaped between two plates of brass were conductors or non-conductors of electricity according to the degree of heaping, and that in the latter case they could be made conductors under the influence of induction. The figure illustrates his experiment. In the circuit of a small battery, he placed a telephone B, a galvanometer C, and two brass plates DE separated by the copper filings. So long as the G. Marconi's method, short-circuit arrangement, F wire dipping into mercury, was open, the galvanometer showed traces of a very feeble current across the filings. But on dipping the wire for a moment into the mercury and then withdrawing it, a sharp click is heard in the telephone, and the galvanometer indicates the passing of a strong current, showing that the filings must now be conductors. This change he traced to the induced current of the telephone coil, the extra current direct. At the moment of opening the short circuit, he repeated this experiment with various powders or filings of metal, and ended by showing that some of them became conductors under the influence of a very feeble spark, while others became so only after being subjected to strong sparks as from an electrical machine. These important observations were published in Tu Nuovo Cemento, 1884 but attracted no attention, and it was only after Professor E. Branly of the Catholic University of Paris had published his results in 1890 that the earlier discoveries of Yarley and Wensti came to be remembered and appreciated at their proper value. Professor Branly's investigations are very clearly described in A la Lumière électrique, May and June 191. As this now classic paper deals with facts which are at the very foundation of the Marconi system, I give some extracts from it in Appendix 100. Here, therefore, I need only say that Branly verified and extended Calzecchi-Wensti's observations, and made the further and for our purpose vital discovery that the conducting power, imparted to filings by electric discharges in their vicinity, cannot at once be destroyed by simply shaking or tapping them. The Branly detector, as constructed by Professor Lodge, is shown in the figure. It consists of an ebonite or glass tube about 7 inches long, half an inch outer diameter, and fitted at the ends with copper pistons, which can be regulated to press on the filings with any required degree of pressure. To bring back the filings to their normal non-conducting state, Lodge applied to the tube a mechanical tapper, worked either by clockwork or by a trembling electrical mechanism. These then, the exciters and the detectors of Hertzian waves, are the bricks and mortar, so to speak, of the Marconi system, and it now only remains to see how they have been shaped and put together to produce a telegraph without connecting wires, which is the realization of the dream of Steinheil in 1838. And first, we must notice 2 or 3 applications, or suggested applications, which preceded the announcement of Marconi's invention. We do so without in the least meaning to detract one iota from the merit, due to the young Irish-Italian inventor, one for we believe the idea was entirely original with him, and was unprompted by any suggestions from outside. The history of the applications of science to art shows us that these applications often occur simultaneously to several persons, and it is therefore not strange that such is the case in the present instance. Sir William Crookes, the eminent chemist and electrician, was, I believe, the first to distinctly foresee the applicability of Hertzian waves to practical telegraphy. In a very interesting paper on some possibilities of electricity, he gives us the following marvelous forecast of the Marconi system. Rays of light will not pierce through a wall, nor, as we know only too well, through a London fog. But electrical vibrations of a yard or more in wavelength will easily pierce such media, which to them will be transparent. Here is revealed the bewildering possibility of telegraphy without wires, posts, cables, or any of our present costly appliances. Granted a few reasonable postulates, the whole thing comes well within the realms of possible fulfillment. At present, experimentalists are able to generate electric waves of any desired length, and to keep up a succession of such waves radiating into space in all directions. It is possible, too, with some of these rays, if not with all, to refract them through suitably shaped bodies acting as lenses, and so to direct a sheaf of rays in any given direction. Also, an experimentalist at a distance can receive some, if not all, of these rays on a properly constituted instrument, and by concerted signals, messages in the Morse code can thus pass from one operator to another. What remains to be discovered is, firstly, simpler and more certain means of generating electrical rays of any desired wavelength from the shortest, say, few feet, which will easily pass through buildings and fogs, to those long waves whose lengths are measured by tens, hundreds, and thousands of miles. Secondly, more delicate receivers which will respond to wavelengths between certain defined limits and be silent to all others. And thirdly, means of darting the sheaf of rays in any desired direction, whether by lenses or reflectors, by the help of which the sensitiveness of the receiver, apparently the most difficult of the problems to be solved, would not need to be so delicate as when the rays to be picked up are simply radiating into space and fading away according to the law of inverse squares. At first sight, an objection to this plan would be its want of secrecy. Assuming that the correspondents were a mile apart, the transmitter would send out the waves in all directions, and it would therefore be possible for anyone living within a mile of the sender to receive the communication. This could be got over in two ways. If the exact position of both sending and receiving instruments were known, the rays could be concentrated with more or less exactness on the receiver. If, however, the sender and receiver were moving about, so that the lens device could not be adopted, the correspondents must attune their instruments to a definite wavelength, say, for example, 50 yards. I assume here that the progress of discovery would give instruments capable of adjustment by turning a screw, or altering the length of a wire, so as to become receptive of waves of any preconcerted length. Thus, when adjusted to 50-yard waves, the transmitter might emit, and the receiver respond to, rays varying between 45 and 55 yards, and be silent to all others. Considering that there would be the whole range of waves to choose from, varying from a few feet to several thousand miles, there would be sufficient secrecy. For the most inveterate curiosity would surely recoil from the task of passing in review all the millions of possible wavelengths on the remote chance of ultimately hitting on the particular wavelength employed by those whose correspondence it was who wished to tap. By coding the message, even this remote chance of surreptitious tapping could be rendered useless. This is no mere dream of a visionary philosopher. All the requisites needed to bring it within the grasp of daily life are well within the possibilities of discovery, and are so reasonable and so clearly in the path of researches, which are now being actively prosecuted in every capital of Europe, that we may any day expect to hear that they have emerged from the realms of speculation into those of sober fact. Even now, indeed, telegraphing without wire is possible within a restricted radius of a few hundred yards. And some years ago, I assisted at experiments where messages were transmitted from one part of a house to another without an intervening wire by almost the identical means here described. In 1893, Nikola Tesla, the lightning juggler, proposed to transmit electrical oscillations to any distance through space by erecting at each end a vertical conductor connected at its lower end to Earth and at its upper end to a conducting body of large surface. Owing to press of other work, this experiment was never tried, and so has remained a bare suggestion. At the Oil Institution, June 1, 1894, and later in the same year at the Oxford meeting of the British Association, Professor Lodge showed how his form of Branly detector could be made to indicate signals at a distance of about 150 yards from the exciter, But at this time, the applicability of his experiment to practical long-distance telegraphy was hardly grasped by him. Referring to this in his work of Hertz, he says, signaling was easily carried on from a distance through walls and other obstacles, an emitter being outside and a galvanometer and detector inside the room. Distance without obstacle was no difficulty, only free distance is not very easy to get in a town. And stupidly enough, no attempt was made to apply any but the feeblest power so as to test how far the disturbance could really be detected. Mr. Rutherford, however, with a magnetic detector of his own invention, constructed on a totally different principle, and probably much less sensitive than a coherer, did make the attempt, June 1896, and succeeded in signaling across half a mile full of intervening streets and houses at Cambridge. Between 1895 and 1896, Messrs. Popoff, Minchin, Rutherford, and others applied the Hertzian method to the study of atmospheric electricity, and their mode of procedure in the use of detectors in connection with vertical exploring rods was much the same as that of Marconi's. Popoff's arrangement especially is so like Marconi's that we are tempted to reproduce it from the Electricità of St. Petersburg for July 1896. The figure shows the apparatus, the action of which is easily understood. The Larth pile relay actuates another circuit, not showy, containing a Richards register which plots graphically the atmospheric perturbations. Professor Popoff's plans were communicated to the Physico-Chemical Society of St. Petersburg in April 1895. And in a further note, dated December 1895, he adds, I entertain the hope that when my apparatus is perfected, it will be applicable to the transmission of signals to a distance by means of rapid electric vibrations, when in fact, a sufficiently powerful generator of these vibrations is discovered. We shall see presently that Popoff was looking in the wrong direction. It was not so much a more powerful generator, which is easily obtained, that was wanted as a more sensitive detector than the ordinary large arrangement which he used. Mr. Marconi, we shall see, supplied this, and in doing so did the main thing necessary to make Popoff's apparatus a practical telegraph. Mr. Priest tells us that in December 1895, Captain Jackson commenced working in the same direction, and succeeded in getting more signals through space before he heard of Marconi. His experiments, however, were treated as confidential at the time, and have not been published. In 1896, the EV, Jervis Smith had a detector made of finely powdered carbon such as is used in incandescent electric lamps for observing atmospheric electricity, and a little later, after Marconi's announcement, he actually applied it to telegraphic purposes over a distance of more than a mile. This form of detector was to a certain extent self-adjusting in that it did not require any tapping device. I now come to Mr. Marconi, whose special application of Hertzian waves to practical telegraphy will be easily understood if my readers have carefully followed me in the preceding pages. His apparatus for short distances with clear open spaces consists of the parts which are shown in diagrammatic form in Figs 37, 38, 39, and 40. The apparatus at the sending station consists of a modified Agee exciter, G. Marconi's method. The figure, Umkorf coil B, a battery of a few cells C, and a Morse key kit. The exciter consists of two solid brass spheres, a B to figure 11 centimeters in diameter and 1 millimeter apart, yielding with a 6-inch spark coil waves of about 25 centimeters long. The spheres are fixed in an oil, tight case of parchment or ebonite, so that an outside hemisphere of each is exposed, the other hemisphere is being immersed in Vaseline oil thickened by the addition of a little plane. The use of oil has several advantages, all of which combine to increase the effect, and therefore the distance at which this effect, CO, can be detected. It keeps the opposing surfaces of the spheres clean and bright. It gives to the electric waves a uniform and regular character, and it reduces the length of these waves to the small limits best adapted for signaling. Two small balls, also of solid brass, a B, are fixed in a line with the large ones, usually about 2 centimeters apart, and are capable of adjustment. The larger the spheres and balls, and the greater the distances separating them, The higher the potential of the spark, and consequently, the greater the distance at which the oscillations are perceptible. The balls of B are connected each to one end of the secondary coil of the room core of apparatus B. The primary wire of the induction coil is excited by the battery C, thrown in and out of circuit by the key K. The efficiency of the sending apparatus depends greatly on the power and constancy of the induction coil. Thus, a coil yielding a 6-inch spark will be effective up to 3 or 4 miles, but for greater distances than this, more powerful coils, as one emitting 20-inch sparks must be used. The various parts of the sending apparatus are generally so constructed and adjusted as to emit per second about 250 million waves of about 1 meter long. At the receiving station, and in the figure, is Marconi's special form of the Branly Lodge detector shown full size in the figure. This is the part which gave him the most trouble. While for laboratory experiments, a detector of little delicacy sufficed to give indications on a sensitive mirror galvanometer, at a distance of a few yards, Mr. Marconi had to seek in G. Marconi's method, arrangement which would respond sufficiently to the very feeble waves which are found at a great distance from the source, so as to allow of the passage of a current strong ALLs, enough to actuate a telegraph relay. His detector consists of a glass tube, 4 centimeters long and 2 millimeters interior diameter, into which 2 silver pole pieces, 1 millimeter apart, are tightly fitted, so as to prevent any scattering of the powder. The small intervening space is filled with a mixture of 96 parts of nickel and 4 of silver, not too finely powdered, and worked up with a trace of mercury. By increasing the proportion of silver powder, the sensitiveness of the detector is increased pro rata, but it is better for ordinary work not to have too great sensitiveness, as the detector then too readily responds to atmospheric electricity and other stray currents. Similarly, the smaller the powder space, the more sensitive is the instrument, but if too small, the action is capricious. The quantity of powder required is, of course, very small, but it must be treated with care. It must neither be too compressed nor too loose. If too tight, the action is irregular, and often the particles will not return to their normal condition, or decohere, as Lodge expresses it, if too loose coherence is slight, and the instrument is not sufficiently sensitive. The best adjustment is obtained when the detector works well under the action of the sparks from a small electric trembler at 1 meter's distance. The tube is then hermetically sealed, having been previously exhausted of air to about 1/2 of an atmosphere. This, though not essential, is desirable as it prevents the oxidation of the powder. In its normal condition, the metallic powder, as already stated, is practically a non-conductor, offering many megomes resistance. The particles, to use Mr. Priest's expressive words, lie higgledy-piggledy anyhow in disorder. They lightly touch each other in a chaotic manner, but when electric waves fall upon them, they are polarized. Order is installed. They are marshaled in serried ranks and press on each other. In a word, they cohere. Electrical continuity is established, and a current passes, the resistance falling from practical insulation to a few ohms or a few hundred ohms according to the energy of the received impacts. Usually it ranges from 100 to 500 ohms. The detector is included in the circuit of 2 electromagnetic impedance or choking coils and a local battery of 1 or 2 Leclanche cells, P, and a fairly sensitive polarized relay as ordinarily used in telegraphy or E. The impedance or choking coils, consisting of a few turns of insulated copper wire on a glass tube containing an iron bar 5 or 6 centimeters long, are intended to prevent the electric energy escaping through the relay circuit. Professor Sylvan L.S. Thompson doubts the efficacy of this contrivance, but Mr. Marconi's experience shows its great utility. Thus, when the coils are removed, all other things remaining the same, the signaling distance is reduced by nearly 1/2. Are resonance plates or wings, copper strips, whose dimensions must be adjusted so as to bring the detector into tune electrically with the exciter. The relay actuates 2 local circuits on the parallel or shunt system, one containing an ordinary Morse instrument M, and the other the tapper SD. The relay and tapper are provided with small shunt coils in S to prevent sparking at the contacts. which would otherwise impair the good working of the detector. The Morse instrument and the tapper may also be connected in series in one circuit, in which case the former may be made to act as a buzzer, the signals being read by sound. Indeed, the Morse machine may be left out altogether, and the signals be read from the sound of the tapper alone. The printing lever of the Morse is so adjusted an easy matter as not to follow the rapid makes and breaks of the local current caused by the action of the tapper. Consequently, although the current in the coils of the Morse is rapidly discontinuous, the lever remains down and prints, so long as the detector is influenced by the waves sent out by the exciter. In this way, the lever gives an exact reproduction of the movements of the distant sending key dots and dashes at the key coming out as dots and dashes in the Morse. The speed at which signaling can be carried on is but little slower than that in ordinary Morse telegraphy, 15 words a minute being easily attained. In practice, the sending part of the apparatus should be screened as much as possible by interposed metal plates from the receiving instruments, so as to prevent local inductive interferences. Or better, the detector may be shut up in a metal box. Third period, the practical, shown in the figure. Reflectors are discarded, which are troublesome and expensive to make and difficult to adjust. One knob of the exciter is connected to a stout insulated wire led to the top of a mast and terminating in a square sheet or a cylinder of zinc or a pennant-like structure of wire netting. For still greater distances, the wire may be flown from a kite or a balloon covered with tinfoil. The other knob of the exciter is connected to a good earth. At the receiving station, the resonance wings of the detector are discarded, and one side is connected to a vertical wire, and the other side to earth, as in the case of the exciter. Of course, in practice, only one vertical wire is required at each station, as by means of a switch. It can be connected with the exciter for sending or with the detector for receiving, as may be necessary. The parallelism of the plates, the raison d'etre of the earth connections, is not yet clearly understood. An earth wire on the exciter for longitude distances is essential, but at the detector it may apparently be dispensed with without any appreciable effect. Breaking the connection does not prove to me that earth does not enter into the effect. It only increases the resistance of the earth connecting medium, which now is not wire, but consists of the walls, floor, table, and baseboard of the instrument. Again, why suppose that sparks are emitted at the top of the vertical wire? Why not also into the ground, giving us a complete closed circuit through the ether above and through the ground below one? If I may hazard an opinion, I would say that the Marconi effect is but on a large scale, an electrical machine effect such as every schoolboy is air, when they were flown high enough, was sufficient to enable the operator to do away with a primary battery. Electrical Engineer, October 1897. This is the Mahalon Loomis idea redivivus, and is as true as another vulgar error, to wit, that Marconi and now Tesla can explode torpedoes and powder magazines at their own sweet will. This, of course, might be done if they could plant a properly adjusted exploding apparatus near the powder. But if they could do this, they could, as Mr. Priest says, do many other funny things. Familiar with? And that it conforms to the same laws and conditions. However this may be, an earth wire, and a good one too, should be used on the detector as well as on the exciter, if only as a protection from lightning. The vertical wire is practically a lightning catcher, and the detector is an excellent lightning guard when connected to earth. But if disconnected from earth and lightning strikes the wire, then we may expect all the disastrous results which follow from a badly constructed or defective lightning detector. The fear, then, that the Marconi apparatus is dangerous may be put aside. Being excellent lightning conductors and lightning guards in one, they may, in my opinion, be safely used, even in a powder magazine. Delicate as the apparatus undoubtedly is, and complicated as it may seem, its action is simplicity itself to the telegraphist, differing only in the kind of electricity and the medium of communication from that of the everyday telegraphs. On depressing the key K the figure to make, say, a dash, induced currents are set up in the secondary coil of the Uhamkorf machine, which pass in sparks across the spark gaps 1, 2, and 3 and out into space at X. The sparks at X set up electric oscillations in the ether, which are radiated into space in waves. On arriving at the receiving station, some of these waves strike the wire, are carried to the detector, which coheres, allowing the local battery to act. The relay closes and the Morse instrument sounds or prints the signal as may be required, the tapper all the while doing its work of decohering. Marconi's first trials on a small scale were made at Bologna, and these proving successful, he came to England and applied for a patent, June 2, 1896. Soon after, in July, he submitted his plans to the postal telegraph authorities. And to his honor be it said, they were unhesitatingly, even eagerly, taken up by Mr. Preece, although, as we have already seen, he was introducing a method of his own. The first experiments in England were from a room in the General Post Office, London, to an impromptu station on the roof, over 100 yards distant, with several walls and sea intervening. Then, a little later, trials were made over Salisbury Plain for a clear open distance of nearly 2 miles. In these experiments, roughly made copper parabolic reflectors were employed, with resonance plates on each side of the detector, see Figs. 37, 39. In May 1897, still more extensive trials were made across the Bristol Channel between Lavernock and Flatholm, 3 to 3 miles, and between Lavernock and Breen Down near Weston-super-Mare, 8 miles. See Tig 21 ante. Here the reflectors and resonance plates were discarded. Earth and vertical air wires were employed, as in the figure, the vertical wires being in the first case 50 yards high, while in the second case kites carrying the wires were had recourse to. The receiving apparatus was set up on the cliff at Lavernock Point, which is about 20 yards above sea level. Here was erected a pole 30 yards high, on the top of which was a cylindrical cap of zinc, 2 yards long and 1 yard diameter. Connected with this cap was an insulated copper wire leading to one side of the detector, the other side of which was connected to a wire led down the cliff and dipping into the sea. At Flatholm, the sending apparatus was arranged, the Ruhmkorff coil used giving 20-inch sparks with an 8-cell battery. On the 10th, May experiments on Mr. Preece's electromagnetic method, already fully described, were repeated, and with perfect success. The next few days were eventful ones in the history of Mr. Marconi. On the Olellouth and 12th, his experiments were unsatisfactory. Worse, they were failures, and the fate of the new system trembled in the balance, and inspiration saved it. On the 13th, the receiving apparatus was carried down to the beach at the foot of the cliff, and connected by another 20 yards of wire to the pole above, thus making a height of 50 yards in all. Result, magic. The instruments, which for 2 days failed to record anything intelligible, now rang out the signals clear and unmistakable, and all by the addition of a few yards of wire. Thus often, as Carlyle says, do mighty events turn on the straw. Professor Slabby of Charlottenburg, who assisted at these experiments, has told us in a few graphic words the feelings of those engaged. It will be for me, he says, an ineffaceable recollection. 5 of us stood around the apparatus in a wooden shed as a shelter from the gale, with eyes and ears directed towards the instruments, with an attention which was almost painful, and waited for the hoisting of a flag, which was the signal that all was ready. Instantaneously, we heard the first tick-tock, and saw the Morse instrument print the signals, which came to us silently and invisibly from the island rock, whose contour was scarcely visible to the naked eye, came to us dancing on that unknown and mysterious agent, the ether. After this, the further experiments passed off with scarcely a hitch, and on the following day, communication was established between Lavernock and Breen Down. The next important trials were carried out at Spezia by request of the Italian government between July 10 and 18. The first 3 days were taken up with experiments between 2 land stations 3 kilometers apart, which were perfectly successful. On the 14th, the sending apparatus being at the arsenal of San Bartolomeo, the receiving instruments were placed on board a tug vessel moored at various distances from the shore. The shore wire was 26 meters high and could be increased to 34 if necessary. The tug wire was carried to the top of the mast and was 16 meters high. The results were unsatisfactory. Signals came, but they were jumbled up with other weird signals which came from the atmosphere. The weather was stormy, in the way which telegraph and telephone operators know so well. On the 15th and 16th, the weather having moderated, better results were obtained, and communication was kept up at distances up to 75 kilometers. On the 17th and 18th, the receiving apparatus was transferred to a warship, ironclad, and with a shore elevation of 34 meters and a ship elevation of 22 meters. Signals were good at all distances up to 12 kilometers, and fairly so at 16 kilometers. During these experiments, it was observed that whenever the funnels, iron masts, and wire ropes of the vessels were in line with the shore apparatus, the detector did not work properly, which was to be expected from the screening property of metals. But another and more serious difficulty was also encountered. When the vessel got behind a point of the land which cut off the view of the shore station, the signals came capriciously, and good working was not established until the shore was again in full view. Here was a difficulty which must be surmounted if the new system was to be of any practical utility. We have seen in our account of the work of Hertz that electric waves pass without appreciable hindrance through doors and walls, and generally non-conducting bodies being only arrested by metals and other conductors. But in practice, when we come to deal with doors and walls in large masses, as trees, buildings, hills, especially if near the vertical wires, they partake of the nature of metals and largely absorb the waves, just as light passes through a thin sheet of glass, but is obscured or third period, the practical. This difficulty is in the nature of things and must always remain. It is surmountable to a very great extent by increasing the height of the vertical wires, terminating with suitable capacity areas, and by increasing the power of the sending and the delicacy of the receiving apparatus. But we speedily reach a limit in these directions, so that as far as one can see at present, the effective distance of the new system must be small compared with the older methods. The figure, which I borrow from Mr. Priest, shows how hills are apparently bridged over. From a long series of experiments in Italy in 1895, Mr. Marconi worked out a law of distance which all his later experience seems to verify. The results, he says, showed that the distance at which signals could be obtained varied approximately as the square of the height of the capacity areas from Earth, or perhaps as the square of the length of the vertical conductors. This law furnishes us with a safe means of calculating what length the vertical wire should be in order to obtain results at a given distance. The law has never failed to give the expected results across deer space in any installation I have carried out, although it usually seems that the distance actually obtained is slightly in excess. I find that, with parity of other conditions, vertical wires 20 feet long are sufficient for communicating 1 mile, 40 feet 4 miles, 80 feet 16 miles, and so on. Professor Ascoli has confirmed this law. And demonstrated mathematically, using Neumann's formula, that the inductive action is proportional to the square of the length of one of the two conductors, if the two are vertical and of equal length, one and in simple inverse proportion of the distance between them. Therefore, the intensity of the induced oscillation does not diminish with the increase of distance if the length of the vertical conductors is increased in proportion, or as the square root of the distance, that is, if the height of the wire is doubled, the possible distance becomes quadrupled. On his return to Germany, after witnessing the Marconi experiments in England, Professor Slaby in September 1897 engaged in some very instructive experiments in the vicinity of Potsdam, first between Matrisson Station and the church at Sacro, 1/6 kilometers, and then between the former place and the castle of Fauninsel, 3 kilometers. I take the following particulars from the electrical engineer, December 3rd, 1897. Professor Slaby recently, at a technical college in Berlin, gave an interesting report of his experiments on telegraphy without wires, or, as he wants it to be called, spark telegraphy. He mentioned an experiment made by himself by which he was able to send by means of one wire 2 different messages simultaneously without interfering with each other. He explained that the continuous current used in ordinary telegraphy is conducted along the middle of the wire, and he proved that electric waves on their way through the ether are attracted by wires which come in their way, and that they travel along the outside of those wires without influencing the interior. In making use of these observations, he succeeded in sending a wave message along the outside of the wire, while another message was proceeding through the center by the continuous current. Professor Slaby says that, in conjunction with Dr. Dietz, he made many experiments with spark telegraphy before Marconi's inventions became known, but did not achieve any important results. After his return, however, from England, he experimented still further. The Emperor of Germany was present at some of these experiments and put a number of sailors and the large royal gardens at Potsdam at his disposal. The receiver was erected at the naval station and the transmitter on Peacock Island. The first experiments gave no result because the coherers used were a great deal too sensitive and contained, among other things, too much silver, and were affected by the electricity in the atmosphere, and in consequence were constantly affected, even when no signals were sent from the sending station. Further experiments showed that the result increased in the same measure as the sensitiveness of the coherer decreased. Professor Slaby uses now very rough and jagged nickel filings which have been carefully cleaned and dried. As the receiving station could not be seen from the island, the sending station was removed to a church a little farther away, and the exciter was put between the columns of the portico, while the mast, which carried the wire, was erected on the spire. The experiments then went very well. When the sending apparatus was put back a little farther into the church, and the wire was put for about a length of 2 yards parallel with the stone slabs of the floor and 1.5 yards above it, it ceased to work properly because the waves seek the earth. Hence, one must not bring the wire too near to the earth, or lay it parallel when near the earth. When the sending apparatus was moved back to the island, it was found that trees near the wire proved an obstacle, because they received the waves. Therefore, the professor says that it is best to so arrange that the wires on the receiver and on the transmitter can be seen from each other. Even the sail of a little boat or the smoke from a steamer cause small interruptions, which make the words more or less indistinct. The waves get through impedimenta and even through buildings, but there is always much loss. In order to make the wire which was placed on the island more visible from the mainland, it was lengthened from 25 to 65 yards, and placed upon a boat on the river. That did not remedy matters, but when the wire on the receiver was also lengthened to 65 yards, very good results followed, showing that the length of the wire is of great importance. Professor Slaby next proceeded early in October to experiment over an open stretch of country, free from all intervening obstacles, between Angsdorf sending station. A distance of 21 kilometers. Captive balloons raised to a height of 300 meters were employed. On the first 2 days, the results were disappointing, and the fault was found to be in the vertical conductors, which consisted of the wire cables holding the balloons. With a double telephone wire, there was a slight improvement, and eventually, on the 7th October, fine insulated copper wire of 46 millimeters diameter was substituted with excellent results. Correspondence was now always good, except when disturbed by atmospheric discharges, the weather being stormy. At such times, the signals were distorted and confused, and often the discharges were so strong as to unpleasantly shock the operators, making it necessary to handle the apparatus with the greatest care. Here is another serious difficulty with which Mr. Marconi has to contend, and from which we see no escape short of total suspension of operations during stormy weather, namely, the great liability to accident and derangement. Not merely from lightning flashes to which all telegraph systems are subject, but from all those other electrical disturbances of the atmosphere which have hitherto been of little account. The greater the distance worked over, the higher must be the conductors, and consequently the greater must be the danger. The apparatus used by Professor Slaby differed somewhat from Marconi's, the following being the more important points. A Weston galvanometer relay, which it is curious to note, is our old friend in modern guise, the Wilkins relay, used by Mr. Wilkins in his wireless telegraph experiments in 1845 too. An ordinary Branly Lodge detector with hard nickel powder only. 3. No impedance or choking coils. The further course of Marconi's experiments is so succinctly given by the chairman of the Wireless Telegraph Company in a recent address, October 7, 1898, that we cannot do better than follow him. A year ago, he says, when this company was started, July 1897, Mr. Marconi happened to be in Italy making experiments for the Italian government and for the king and queen at the Quirinal. On his return to this country, the first long-distance trial was made between Bath and Salisbury. The receiver in this case was given to a post office official who went to Bath and by himself rigged up a station at which he received signals 34 miles distant from where they were sent at Salisbury. After this, we put a permanent station at Allambay, Isle of Wight. This station at first was used in connection with a small steamer that cruised about in the neighborhood of Bournemouth, Boscombe Pool Bay, and Swanage, a distance of 18 miles from the Needles Hotel station, with which it was in constant telegraphic communication. Various exhibitions were given later, one at the House of Commons, where a station was erected, and another station at St. Thomas's Hospital opposite, May 1898. Within an hour of the time our assistants arrived to put up the installation, the system was at work. We had many exhibitions at our offices, at which a number of people attended, amongst others Mr. Brinton, a director of the Donald Curry line of steamers, who asked if we could report a ship passing our station. This was done. The ship was the Carisbrooke Castle on her first voyage out, and as she passed the Needles, a message reporting the fact was wirelessly telegraphed to Bournemouth, and there put on the ordinary telegraph wires for transmission to Mr. Brinton. After this, Lord Kelvin visited our station at Allambay and expressed himself highly pleased with all he saw. He sent several telegrams via Bournemouth to his friends, for each of which he insisted on paying 1 shilling royalty, wishing in this way to show his appreciation of the system and to illustrate its fitness for commercial uses. The following day, the Italian ambassador visited the station. Among other messages, he sent a long telegram addressed to the aide-de-camp to the King of Italy. As it was in Italian, and as Mr. Marconi's assistant at Bournemouth had no knowledge of that language, it may be taken as a severe test, as in fact a code message. The telegram was received exactly as it was sent. Previously, we had a display for the Electrical Review and the Times, both of which papers sent representatives. They put the system to every possible test, and among others, sent a long code message which had to be repeated back. In their reports, they stated that this was done exactly as sent. Following this, in July last, 1898, we were requested by a Dublin paper, the Daily Express, to report the Kingstown Regatta. In order to do this, we erected a Yealon station at Kingstown and another on board a steamer which followed the yachts. A telephone wire connected the Kingstown station with the Daily Express offices, and as the messages came from the ship, they were telephoned to Dublin and published in successive editions of the evening papers. After this, Mr. Marconi was requested to put up a station at Osborne to connect with the Prince of Wales' yacht, Osborne. Bulletins of the Prince's health, His Royal Highness, as we all know, met with a lamentable accident just before then, were reported to Her Majesty. Not only that, but the royalties made great use of our system during the Cowes Week. After the regatta had concluded, the prince wished to cruise about, and he did so as far as Bembridge on one occasion. The next day they went over to the Needles, at the opposite side of the Isle of Wight. The royal yacht was kept in telegraphic communication with the Osborne station on the first day. On the second occasion, they were able not only to communicate with Osborne, but also with our station at the Needles Hotel. They rang up the Needles Hotel when 7 or 8 miles away, and immediately had a reply, although about the highest land in the Isle of Wight lay between the royal yacht and the Needles Hotel station. Within the last few days, we have had to move our station at Bournemouth 4 miles farther west, where we have put up the same instruments, the same pole, and everything at the Haven Hotel pool, which is 18 miles from Allambay. This increase of distance has no detrimental effect on our work. In fact, it seems rather easier, if anything, to receive signals at the Haven Hotel than at our former station. Thus, the height of the conductor at Bournemouth was 150 feet, but this is now reduced to 100 feet, which is a very great improvement. We have sent our assistants to various countries to make demonstrations in connection with our patent rights. And lately, we sent one of our staff to Malta, where some excellent experiments were carried out for the government officials. The Marconi invention is the only electric telegraph by means of which a moving object can be kept in communication with any other moving object or a fixed station, and therefore anyone can see the great use of the invention, not only to the Royal Naval Authorities, but also to the mercantile marine. A ship fitted with Mr. Marconi's apparatus can not only keep in telegraphic communication with the shore up to any reasonable distance, it has been thoroughly tested up to 25 miles off the shore. But ships can also, if properly equipped, be warned of approaching danger or their proximity to dangerous coasts, which are fitted with the wireless apparatus. The weather has no effect at any rate, no adverse by reverting, however, to the original form of the apparatus, discarding vertical wires, and by revolving a metallic screen about the detector until the position of maximum effect is obtained, the ship could possibly fix the direction whence come the rays. But this, though important, is not enough. As the ship does not know her distance from the rock, it does not tell her enough as to her exact position. The distance might possibly be ascertainable if the detector could be calibrated to varying degrees of electric energy, a very great difficulty, a fact. The only thing we find is that on a foggy day, when a place is obscured, everything is made easier for us. Our worst electrical day is a fine, bright, sunny day in July, when everything can be seen. But directly everything becomes obscured, the facilities of wireless telegraphy are increased. I had a telegram handed to me just as I came in, querying if the government or the post office were not, as has been reported, trying to stop us. So far from that being the case, they have actually requested us to put the system up between Guernsey and Sark, and they have offered us a post office at each end for the instruments. That matter is occupying our attention, and we shall go on with it at once. Also, as we wish to work the thing in France as well as in England, we now intend to put up a station between Calais and Dover. There is not the least doubt of success being achieved because we are doing a parallel distance today without the slightest difficulty. The sea between Calais and Dover is the same sea as between the Isle of Wight and Poole. So the things being equal in both cases, we may expect the same success between Calais and Dover as between the other points. It has been objected to the Marconi system that, with the removal of the reflectors and the resonance wings on the detectors, the condition of privacy in telegrams no longer holds good. Since anyone provided with the necessary apparatus can receive the signals at any point within the circle which the sending station is the center, and the receiving station the radius. Another, and in some cases more serious, objection is that anyone, by erecting a wire or wires in the vicinity of a Marconi station, can propagate therefrom Hertzian waves, which by interference will so confuse the effects as to make correct signaling impracticable. It is not even necessary to propagate counter waves. A large sheet of metal, or several such sheets, erected high in air in line with the stations and connected by a wire to the earth, will intercept much of the energy, and the more so as it is near to either of the stations and at right angles to the direction of the waves. Thus, if used for naval or military purposes, an enemy could either tap the dispatches or render them unintelligible at pleasure. The latter objection is from the nature of things unavoidable, and in practice must limit the application of the system to lines of communication sufficiently apart as not to interfere with one another. The first objection, however, can be obviated by reverting to the condition of syntony or resonance, and it is in this direction that improvements may soon be expected. Dr. Oliver Lodge, FRS, the distinguished professor of physics, University College, Liverpool, and the great disciple and expounder of Hertz in England, has long been engaged on this problem of a Hertzian wave telegraph, more especially with a view of securing syntony in the sending and receiving apparatus, and thereby limiting the communications to similarly attuned instruments, the absence of which selective character is at present one of the great drawbacks of the Marconi system. We have seen that as early as June 1, Professor Lodge had exhibited apparatus which was effective for signaling on a small scale, but as he says, stupidly enough, no attempt was then made to apply any but the feeblest power. So as to test how far the disturbance could really be detected, there remained no doubt a number of points of detail and considerable improvements in construction if the method was ever to become practically useful. Them are embodied in his patent, number 11575 of May 10, 1897, improvements in syntonized telegraphy without line wires, as capacity areas, spheres, or square plates of metal may be employed. But for the purpose of combining low resistance with large electrostatic capacity, cones or triangles are preferred, with the vertices adjoining and their larger areas spreading out into space. Or a single insulated surface may high law H be used in conjunction with the earth, or conductors embedded in it, constituting the other capacity area, as radiation from these surfaces is greater in the equatorial than in the axial direction. So when signaling in all directions is desired, the axis of the emitter should be vertical. Moreover, radiation in a horizontal plane is less likely to be absorbed during its passage over partially conducting earth or water. The figure shows the arrangement for long-distance signaling. HH1 are large triangular sheets of metal, which by means of suitable switches, not shown, can be connected to the sending or the receiving apparatus as desired. Those on the left-hand side of the figure are shown in connection with polished knobs, H2, H3, which form the adjustable spark gap of the exciter. Between each capacity area and its knob is inserted a self-inductance coil of thick wire or metallic ribbon, CH the figure, suitably insulated, the object of which is to prolong the electrical oscillations in a succession of waves, and thereby obtain a definite frequency or pitch, rendering syntony possible. Since exactitude of response depends on the fact that with the emission of a number of successive waves, the feeble impulse at the receiving station is gradually strengthened, till it causes a perceptible effect. On the well-known principle of sympathetic resonance, the capacity areas and inductance coils are exactly alike at the two communicating stations, so as to have the same frequency of electrical vibration. This frequency can be altered either by varying the capacity of the Leyden jars used in the exciting circuit, or by varying the number and position of the inductance coils, or by varying both in the proper degree, thus permitting only those stations whose rate of oscillation is the same to correspond. To actuate the exciter, a Kumkorf coil may be used, or a Tesla coil, a Wimshurst machine, or any other high-tension apparatus. The figure shows the details of the arrangement for exciting and detecting the electric waves. When used as a transmitter, the receiving circuit is disconnected from the capacity areas by a suitable switch, not shown. Let us first consider the arrangement as a transmitter. Putting the Kumkorf coil A in action, it charges the Leyden jars JJ, whose outer coatings are connected, first through a self-inductance third period, the practical. Coil H5 of fairly thin wire so as to permit of thorough charging of the jars, and second to the supply gaps H6, H7. When the jars are fully charged to sparking point, sparks occur at the starting gap H8. These precipitate sparks at the supply gaps, which evoke electrical charges in the capacity areas HH1. These charges surge through the inductance coils H and spark into each other across the discharge gap between the knobs H2, H3. This last discharge, according to Professor Lodge, is the chief agent in starting the oscillations which are the cause of the emitted waves. But it is permissible to close the discharge gap, and so leave the oscillations to be started by the sparks at the supply gaps only, whose knobs must then be polished and protected from ultraviolet light, so as to supply the electric charge in as sudden a manner as possible. When used as a receiver, the discharge gap is bridged over by a suitable cutout, and connection is made with the G. Marconi's method. Receiving circuit as shown on the top of the figure. As detector, Lodge uses 1. His own original form of coherer, the figure, wherein a metallic point rests lightly on a flat metallic surface. Or for instance, a needle point of steel or platinum making light contact with a steel or aluminium bar like a watch spring, fixed at one end P and delicately adjustable by a micrometer screw Q, so as to regulate the pressure at the point N or 2. A Branly tube filled with selected iron filings of uniform size, sealed up in a good vacuum, and with the electrodes, which are of platinum, reduced to points a short distance apart. His latest form of the Branly coherer is shown full size in the figure, and is said to be exceedingly sensitive and certain in its action, especially in a very high vacuum. A is a glass tube held tightly by ebonite supports. B. C is a pocket or reservoir for spare filings, which can be added to or taken from the effective portion as required by inverting the tube. D are the silver electrodes immersed in the filings, which are, as before, of carefully selected iron of thide period, the practical, uniform size as nearly as possible. E is one of the terminals of the silver electrodes, the other of which is hidden from view. The instrument is secured by the clamp screw F to any convenient support, to which the tapping or decohering apparatus is applied. When an electric wave from a distant exciter arrives and stimulates electric vibrations in the syntonized capacity areas, the electrical resistance of the coherer suddenly and greatly falls, and permits the small battery F, the figure, to actuate a relay G or a telephone or other telegraphic instrument, to break contact or to restore the original great resistance of the coherer. Any form of mechanical vibration suffices as a clock or a tuning fork, or a cogwheel, as in the figure, or other device for causing a shake or motion by a spring, tremor, and kept in or weight or by electrical means. Indeed, the mere motion of any clockwork attached to the coherer stand will suffice, an exceedingly slight, almost imperceptible tremor being all that is usually required. Usually, the coherer is arranged in simple series with the battery and telegraphic instrument, and is so joined to the capacity areas as to include in its circuit the self-inductance coils, an arrangement which Professor Lodge considers of great advantage, or, as he says, an improvement on any mode of connection that had previously been possible without these coils. The patent specification figures and describes another way, viz., enclosing the inductance coils in an outer or secondary coil, constituting a species of transformer, and making this coil part of the coherer circuit. In this case, the coherer is stimulated by the waves in the secondary coil rather than primarily by those in the inductance coils, which, with their capacity areas, are thus left free to vibrate without disturbance from attached wires. In all cases, it is permissible and sometimes desirable to shunt the coils of the telegraphic instrument G by means of a fine wire or other non-inductive resistance, coil W, in order to connect the coherer more effectively and closely to the capacity areas. At the Royal Society Conversation on May 11, 1898, a complete set of Lodge's apparatus was shown in action, in which certain modifications in the signaling and recording parts were introduced at the suggestion of Dr. Alexander Muirhead. Instead of the ordinary Morse key, Muirhead's well-known automatic transmitter with punch tape was employed at one end of the suite of rooms, and a siphon recorder as the receiving instrument at the other end. The recorder was so arranged as to print, not as usually zigzag traces, but the needle working between stops, a momentary deflection mark for a dot, and a longer continued mark for a dash. The siphon recorder is so quick in its responses that it indicates each one of the torrent of sparks emitted from the sending apparatus. Hence, a dash is not merely a deflection held over, but is made up of a series of minute vibrations. And even a dot is seen to consist of similar vibrations, though of course of a lesser number. If the speed of signaling is slow and the recorder tape moves slowly, these vibrations appear as actual dots and dashes, but each signal, when examined with a microscope, is seen to consist of a short or long series of lines representing the constituent vibrations. At a slow rate of working, the signals can thus be got with exceeding clearness. But for actual signaling, this is not at all necessary, and it is possible to attain a high speed, making such brief contacts that a single deflection of the recorder needle indicates a dot, and 3 consecutive deflections a dash. The paper thus marked does not look like the ordinary record, but more resembles the original Morse characters as depicted on AN 409 of Schaffner's telegraph manual, and is easily legible with a little practice. An ordinary telephone was also available as a receiver. connected through a transformer coil in which the dots and dashes were heard very clearly and distinctly. The apparatus is reported to have worked well, except at the high speeds, when it occasionally missed fire, and did not seem to be in the least affected by any of the numerous electrical exhibits in the neighborhood, although some of them must have set up considerable radiation of Hertzian waves, based on the same principles, viz., the emission of electric waves at one place and their detection by some form of coherer at another place. There is naturally a similarity in the outlines of the Lodge system and that of Marconi for short distances, where vertical wires are not used, as depicted in the figure ante, the differences of arrangement and detail only. But they appear to be fraught with some important consequences. In the first place, Professor Lodge claims that his arrangement of the sending apparatus is a more persistent exciter in that it emits a longer train of longer waves, one which, by acting cumulatively on the detector, breaks down its insulation, when more powerful but fewer impulses of shorter waves might be inoperative. Then in the next place, this element of persistency permits of the use of synchronizing contrivances, by means of which the rate of oscillation of any desired set of instruments can be accurately attuned, so that only those instruments can correspond without affecting or being affected by other sets tuned to a different frequency, thus securing the undoubted advantage of privacy in the communications. Lodge's arrangement has worked well in the laboratory and lecture room, but he does not appear to have tried it, which is a pity, over any considerable distance, so that it remains to be seen how far he can go without having recourse to vertical wires, which Marconi finds so essential for practical work over distances of more than 2 or 3 miles. A few words as to the future by way of conclusion, and our task is completed. On this point, we find some recent remarks of Professor Sylvanus Thompson, so appropriate that we quote them in full as being more authoritative than anything we could ourselves say. Professor Thompson has thoroughly studied the subject, and therefore speaks by the card. It has been shown, he says, that there are 3 general methods of transmitting electric signals across space. All of them require base lines or base areas. The first, conduction, requires moist earth or water as a medium, and is for distances under 3 miles the most effective of the 3. The second, induction, is not dependent upon earth or water, but will equally well cross air or dry rock. The third, electric wave propagation, requires no medium beyond that of the ether of space, but is interfered with by interposed things such as mass or trees. Given proper baselines or base areas, given adequate methods of throw-wing electric energy into the transmitting system, and sufficiently sensitive instruments to pick up and translate the signals, it is possible, in my opinion, so to develop each of the 3 methods that by any one of them it will be possible to establish electric communication between England and America across the intervening space. It is certainly possible either by conduction or by induction. Whether by waves, I am somewhat less certain. Conduction might very seriously interfere with other electric agencies, since the waste currents in the neighborhood of the primary baseline would be very great. It is certainly possible either by conduction or induction to establish direct communication across space with either the Cape or India or Australia under the same assumptions as before, and at a far less cost than that of a connecting submarine cable. Instruments which operate by means of alternating currents of high frequency, like Mr. Langdon Davies's phonophore, are peculiarly liable to set up disturbance in other circuits. A single phonophore circuit can be heard in lines 100 miles away. When this first came to my notice, it impressed me greatly, and coupled in my mind with the Ferranti incident mentioned above, see note, ante, caused me to offer to one of my financial friends in the city some 8 years ago to undertake seriously to establish telegraphic communication with the Cape, provided £10 were forthcoming to establish the necessary basal circuits in the 2 countries, and the instruments for creating the currents. My offer was deemed too visionary for acceptance. The thing, however, is quite feasible. The one necessary thing is the adequate baseline or area. All the rest is detail. And attendant, we have the Marconi system, which has been proved to be practicable up to 35 miles, and within this limit there ought to be a wide and useful field for activity Thus, many outlying islands are within this distance from each other and from the continents, with which communication at all times has hitherto been practicable only by the use of cables, which are always costly to make and lay, and often costly to keep in repair. Here, especially between places where the traffic is not great, is a large field to be occupied as cables grow old and fail. Then we have just seen from the address of the chairman of the Wireless Telegraph Company that negotiations are going on with Lloyd's, which, if carried into practical effect, will result in an extensive application for signaling between Lloyd stations and outward and inward bound vessels passing in their vicinity. Indeed, it is not rash to predict that the lighthouses and lightships around the coasts, not only of the British Isles, but of all countries, will in time be supplied with wireless telegraphs, keeping up constant correspondence with all who go down to the sea in ships. Then again, there is the application to intercommunication between ships at sea. Ships carrying the Marconi apparatus can carry on a definite conversation with the occupants of lighthouses and lightships and each other. It will readily be seen that this might, in many cases, be far more serviceable than the few light signals now obtainable, or the signaling by flags, a tedious process at best, and one that is often full of uncertainty, if not of a positive. Turning from sea to land, we find, for the reasons we have already indicated, a more circumscribed field of application, at all events until means are devised for focusing the electric rays and rendering the apparatus syntonic. But even then, although by these means we will be able to record messages only where intended, there still remain cross-interferences of which I fear we can never be rid, and therefore we can never use the system in a network of lines as now, where wires recross and overlap each other in all ways and directions. The waves of electricity, like waves of light and sound in similar circumstances, would so interfere with each other that the result would be chaos. Therefore, wireless telegraphy can only be used in lines removed from each other's disturbing influences, as in sparsely populated countries and undeveloped regions. However, many cases of impromptu means of communication arise where, as Professor Lodge says, it might be advantageous to shout the message, spreading it broadcast to receivers in all directions, and for which the wireless system is well adapted, seeing that it is so inexpensive and so easily and rapidly installed, such as for army maneuvers, for reporting races and other sporting events, and generally for all important matters occurring beyond the range of the permanent line. But for the regular daily correspondence of a nation with its lines ramifying in all directions and carrying enormous traffics, the Marconi system is not adapted, no more than any other wireless method that has been proposed, or is likely to be invented. So, for a long time to come, we must keep to our present telegraphic and telephonic wires, using the wireless telegraph as an adjunct for special cases and contingencies, such as I have mentioned. Postscript. April 17th, 1899. On the 27th of last month, communication was established by the Marconi system between England and France. As all the London daily papers of March 29 and 30 contain full and glowing accounts of this installation, it may not be necessary to do more than to refer my readers to these reports. Still, I think it desirable, so as to bring my record quite up to date, to add these few words as the book is passing through the press. On this side of the channel, the operations took place, by permission of the Trinity House, in a little room in the front part of the engine house, from which the power is derived for the South Foreland lighthouses. The house is on the top of the cliffs overlooking the channel. The demonstrations are being conducted for the benefit of the French government, who have the system under observation. And besides Signor Marconi, there were present at the Foreland yesterday Colonel Comte du Bontavis de Haussy, French military attaché in England, Captain Fahie, representing the French government, and Captain Fearon, French Istival attaché in England. During the afternoon, a great number of messages in French and English crossed and recrossed between the little room at the South Foreland and the Chalet d'Artois at Wimereux near Boulogne. The whole of the apparatus stood upon a small table, about 3 feet square, in the center of the room. Underneath the table, the space was fitted with about 50 primary cells. A 10-inch induction coil occupied the center of the table. The spark is 1 centimeter long, or about 3/4 of an inch. The pole off the top of which the current went into space is 150 feet high. The length of spark and power of current were the same as used for communication with the East Goodwin lightship, a fact which seems remarkable when it is considered that the distance over which the messages were sent yesterday was nearly 3 times as great. The greater distance is compensated for by the increased height of the pole. Throughout the whole of the messages sent yesterday, there was not once a fault to be detected. Everything was clearly and easily recorded. The rate of transmission was about 15 words a minute. The first international press message sent by the new system was secured by the Times and is as follows. Wynkoop, March 28th. Communication between England and the continent was set up yesterday morning by the Marconi system of wireless telegraphy. The points between which the experiments are being conducted are South Foreland and Wimereux, a village on the French coast 2 miles north of Boulogne, where a vertical standard wire, 150 feet high, has been set up. The distance is 32 miles. The experiments are being carried on in the Morse code. Signor Marconi is here conducting the trials and is very well satisfied with the results obtained. This message has been transmitted by the Marconi system from Wimereux to the Foreland. Other demonstrations for Mr. Marconi will no longer permit us to call them experiments, and rightly. 64 miles. Between Nice and Cape Corso in Corsica, over 100 miles. Between the South Foreland and the Eiffel Tower, about 230 miles. And finally, between England and America, which, as shown in the first period of this history, was the dream of the earliest experimenters in wireless telegraphy. A press telegram of April 12 says, the Wireless Telegraph Company had been approached by the representative of a proposed syndicate, which desires to acquire the sole rights of establishing wireless telegraphic communication between England and America. The directors of the company will consider the matter at their first meeting, which is fixed for an early date. Thus I end my task as I began it, with a dream. The self-same dream, as to its realization in the distant future, who can say nay? There are more things in heaven and earth, Horatio, than are dreamt of in our philosophy. In conclusion, I give a few extracts from a letter to Times, April 3, 1899, of Professor Fleming of the University College, London. Professor Fleming is an expert in electrical science, and therefore his views may be taken as representing the last word on our subject. To the editor of the Times, Sir, during the last few days I have been permitted to make a close examination of the apparatus and methods being employed by Signor Marconi in his remarkable telegraphic experiments between South Foreland and Boulogne, and at the South Foreland lighthouse have been allowed by the inventor to make experiments and transmit messages from the station there established both to France and to the lightship on the Goodwin Sands, which is equipped for sending and receiving ether wave signals. Throughout the period of my visit, messages, signals, congratulations, and jokes were freely exchanged between the operators sitting on either side of the channel, and automatically printed down in telegraphic code signals on the ordinary paper slip at the rate of 12 to 18 words a minute. Not once was there the slightest difficulty or delay in obtaining an instant reply to a signal sent. No familiarity with the subject removes the feeling of vague wonder with which one sees a telegraphic instrument merely connected with a length of 150 feet of copper wire run up the side of flagstaff begin to draw its message out of space and print down and dot and dash on the paper tape the intelligence ferried across 30 miles of water by the mysterious ether. I cannot help thinking that the time has arrived for a little more generous appreciation by his scientific contemporaries of the fact that Signor Marconi has by minute attention to detail, and by the important addition of the long, vertical air wire, translated one method of space telegraphy out of the region of uncertain, delicate laboratory experiments and placed it on the same footing as regards certainty of action and ease of manipulation, so far as the present results show, as any of the other methods of electric communication employing a continuous wire between the two places. This is no small achievement, The apparatus, moreover, is ridiculously simple and not costly. With the exception of the flagstaff and 150 feet of vertical wire at each end, he can place on a small kitchen table the appliances, costing not more than £100 in all, for communicating across 30 or even 100 miles of channel. In the presence of the enormous practical importance of this feat alone, and of the certainty with which communication can now be established between ship and shore without costly cable or wire, the scientific criticisms which have been launched by other inventors against Signor Marconi's methods have failed altogether in their appreciation of the practical significance of the results he has brought about. The public, however, are not in the least interested in learning the exact meed of merit to be apportioned to various investigators in the upbuilding of this result. They do, however, want to know whether the new method of communication across the channel, established by the expenditure of a few £100s, will take the place to any considerable extent of submarine cables, which have cost many thousands of pounds to lay and kept. They do also desire to learn what reasons, if any, will prevent every lighthouse and lightship round our coast from being forthwith furnished with the necessary apparatus for placing it in instantaneous and secure connection with the mainland. They also hope to hear that the methods can be applied to enable ships to be able, in addition, to communicate instantly, in case of need, with shore stations, to understand how far these things can be done, and to appreciate the necessary or present limitations of the method. It is requisite to explain that each vertical wire or rod connected to a Marconi receiving or sending apparatus has a certain sphere of influence. Signor Marconi has proved by experiment up to certain limits that the distance to which effective signaling extends varies as the square of the height of the rod. A wire 20 feet high carries the effective signal 1 mile, 40 feet high 4 miles, 80 feet 16 miles, and so on. Up to the present time, he has not yet discovered any method of shielding any particular rod so as to render it responsive only to signals coming from one station, and not from all others within its sphere of influence. In spite, however, of what has been said, there is no inherent impossibility in attaining this desired result. At present, all signals sent from the South Foreland to France affect the receiver on board the Goodwin lightship. But this offers no difficulty. In an ordinary electric bell system in a hotel, the servant recognizes the room from which the signal conies by means of a simple apparatus called an indicator. And very similar arrangement can be applied to distinguish the origin of an ether wave signal when several instruments are at work in a common region. Subsequent inventions, as also perhaps the promulgation of some necessary Board of Trade regulations for the use of the ether, will prevent official ether wave receivers from being disturbed by vagrant electric waves sent out by unauthorized persons in their neighborhood. The practical upshot, however, of the matter is that at present, if more than 2 stations are not established within certain regions, these stations, pair and pair, can communicate with each other freely and regularly by means of ether wave signals sent out and received by long vertical rods or wires. No state of the atmosphere and neither darkness nor storm interrupts, so far as yet found, the freedom of communication. Up to the present time, none of the other systems of wireless telegraphy employing electric or magnetic agencies has been able to accomplish the same results over equal distances, without denying that much remains yet to be attained, or that the same may be effected in other ways. It is impossible for anyone to witness the South Foreland and Boulogne experiments without coming to the conclusion that neither captious criticism nor official lethargy should stand in the way of additional opportunities being afforded for a further extension of practical experiments. Wireless telegraphy will not take the place of telegraphy with wires. Each has a special field of operations of its own. But the public have a right to ask that the fullest advantage shall be taken of that particular sendee which ether wave telegraphy can now render in promoting the greater safety of those at sea, and that in view of our enormous maritime interests. This country shall not permit itself to be outtraced by others in the peaceful contest to apply the outcome of scientific investigations and discoveries in every possible direction to the service of those who are obliged to face the perils of the sea. If scientific research has forged a fresh weapon with which in turn to fight nature, red in tooth and claw, all other questions fade into insignificance in comparison with the inquiry, how we can take the utmost advantage of this addition to our resources. I am in C.J. Fleming University College, London. Chapter 25, Appendix A. The relation between electricity and light. The collation between electricity and light before and after Hertz, before Hertz. Substance of a lecture by Professor Oliver Lodge, London Institution, December 16, 1880. Ever since the subject on which I have to speak tonight was arranged, I have been astonished at my own audacity in proposing to deal, in the course of 60 minutes, with a subject so gigantic and so profound that a course of 60 lectures would be inadequate for its thorough and exhaustive treatment. I must therefore confine myself to some few of the most salient points in the relation between electricity and light, and I must economize time by plunging at once into the middle of the matter without further preliminary. What is electricity? We do not know. We cannot assert that it is a form of matter, neither can we deny it. On the other hand, we cannot certainly assert that it is a form of energy, and I should be disposed to deny it. It may be that electricity is an entity per se, just as matter is an entity per se. Nevertheless, I can tell you what I mean by electricity by appealing to its known behavior. Here is a voltaic battery. I want you to regard it and all electrical machines and batteries as kinds of electricity pumps, which drive the electricity along through the wire very much as a water pump can drive water along pipes. While this is going on, the wire manifests a whole series of properties, which are called the properties of the current, to make a magnet. Then, we only need a current of electricity flowing round and round in a whirl. A vortex or whirlpool of electricity is in fact a magnet, and vice versa. And these whirls have the power of directing and attracting other previously existing whirls according to certain laws, called the laws of magnetism. And moreover, they have the power of exciting fresh whirls in neighboring conductors and of repelling them according to the laws of diamagnetism. The theory of the actions is known, though the nature of the whirls, as of the simple streams of electricity, is at present unknown. So much for what happens when electricity is made to travel along conductors, that is, when it travels along like a stream of water in a pipe, or spins round and round like a whirlpool. But there is another set of phenomena, usually regarded as distinct and of another order, but which are not so distinct as they appear, which manifest themselves when you join the pump to a piece of glass or any non-conductor and try to force the electricity through that. You succeed in driving some through, but the flow is no longer like that of water in an open pipe. It is as if the pipe were completely obstructed by a number of elastic partitions or diaphragms. The water cannot move without straining and bending these diaphragms, and if you allow it, these strained partitions will recover themselves and drive the water back again. Here was explained the process of charging a Leyden jar. The essential thing to remember is that we may have electrical energy in two forms, the static and the kinetic. And it is therefore also possible to have the rapid alternation from one of these forms to the other called vibration. Now we will pass to the second question. What do you mean by light? And the first and obvious answer is everybody knows. And everybody that is not blind does know to a certain extent. We have a special sense organ for appreciating light, whereas we have none for electricity. Nevertheless, we must admit that we really know very little about the intimate nature of light, very little more than about electricity. But we do know this, that light is a form of energy, and moreover that it is energy rapidly alternating between the static and the kinetic forms, that it is, in fact, a special kind of energy of vibration. We are absolutely certain that light is a periodic disturbance in some medium, periodic both in space and time. That is to say, the same appearances regularly recur at certain equal intervals of distance at the same time, and also present themselves at equal intervals of time at the same place. That, in fact, it belongs to the class of motions called by mathematicians undulatory or wave motions. Now, how much connection between electricity and light have we perceived in this glance into their natures? Not much, truly. It amounts to about this, that on the one hand, electrical energy may exist in either of two forms, the static form, When insulators are electrically strained by having had electricity driven partially through them, as in the Leyden jar, which strain is a form of energy, because of the tendency to discharge and do work, and the kinetic form, where electricity is moving bodily along through conductors or whirling round and round inside them, which motion of electricity is a form of energy, because the conductors and whirls can attract or repel each other. On the other hand, light is the rapid alternation of energy from one of these forms to the other, the static form where the medium is strained to the kinetic form when it moves. It is just conceivable then that the static form of the energy of light is electrostatic, that is, that the medium is electrically strained, and that the kinetic form of the energy of light is electrokinetic, that is, that the motion is not ordinary motion but electrical motion. In fact, that light is an electrical vibration, not a material one. On November 5th last year, there died at Cambridge a man in the full vigor of his faculties. Such faculties as do not appear many times in a century, whose chief work had been the establishment of this very fact, the discovery of the link connecting light and electricity, and the proof, for I believe that it amounts to a proof, that they are different manifestations of one and the same class of phenomena, that light is in fact an electromagnetic disturbance. The premature death of James Clerk Maxwell is a loss to science which appears at present utterly irreparable, for he was engaged in researches that no other man can hope as yet adequately to grasp and follow out. But fortunately, it did not occur till he had published his book on electricity and magnetism, one of those immortal productions which exalt one's idea of the mind of man, and which has been mentioned by competent critics in the same breath as the Principia itself. The main proof of the electromagnetic theory of light is this: the rate at which light travels has been measured many times and is pretty well known. The rate at which an electromagnetic wave disturbance would travel, if such could be generated, and Mr. Fitzgerald of Dublin thinks he has proved that it cannot be generated directly by any known electrical means, can be also determined by calculation from electrical measurements. The two velocities agree exactly. The first glimpse of this splendid generalization was caught in 1845, 35 years ago, by that prince of pure experimentalists, Michael Faraday. His reasons for suspecting some connection between electricity and light are not clear to us. In fact, they could not have been clear to him. But he seems to have felt the conviction that if he only tried long enough and sent all kinds of rays of light in all possible directions across electric and magnetic fields in all sorts of media, he must ultimately hit upon something. Well, this is very nearly what he did. With a sublime patience and perseverance which remind one of the way Kepler hunted down guess after guess in a different field of research, Faraday combined electricity or magnetism and light in all manner of ways, and at last he was rewarded with a result, and a most out-of-the-way result it seemed. First, you have to get a most powerful magnet and very strongly excite it. Then you have to pierce its two poles with holes, in order that a beam of light may travel from one to the other along the lines of force. Then, as ordinary light is no good, you must get a beam of plain polarized light and send it between the poles. But still no result is obtained until finally you interpose a piece of a rare and out-of-the-way material, which Faraday had himself discovered and made, a kind of glass which contains borate of lead, and which is very heavy or dense, and which must be perfectly annealed. And now, when all these arrangements are completed, what is seen is simply this, that if an analyzer is arranged to stop the light and make the field quite dark before the magnet is excited, then directly the battery is connected and the magnet called into action, a faint and barely perceptible brightening of the field occurs, which will disappear if the analyzer be slightly rotated. The experiment was shown. Now, no wonder that no one understood this result. Faraday himself did not understand it at all. He seems to have thought that the magnetic lines of force were rendered luminous, or that the light was magnetized. In fact, he was in a fog and had no idea of its real significance, nor had anyone. Continental philosophers experienced some difficulty and several failures before they were able to repeat the experiment. It was in fact discovered too soon, and before the scientific world was ready to receive it. and it was reserved for Sir William Thomson briefly, but very clearly to point out, and for Clerk Maxwell more fully to develop its most important consequences. This is the fundamental experiment on which Clerk Maxwell's theory of light is based. But of late years, many fresh facts and relations between electricity and light have been discovered, and at the present time they are tumbling in great numbers. It was found by Faraday that many other transparent media, besides heavy glass, would show the phenomenon if placed between the poles, only in a less degree. And the very important observation that air itself exhibits the same phenomenon, though to an exceedingly small extent, has just been made by Kundt and Röntgen in Germany. Dr. Kerr of Glasgow has extended the result to opaque bodies and has shown that if light be passed through magnetized iron, its plane is rotated. The film of iron must be exceedingly thin because of its opacity. And hence, though the intrinsic rotating power of iron is undoubtedly very great, the observed rotation is exceedingly small and difficult to observe. And it is only by very remarkable patience and care and ingenuity that Dr. Kerr has obtained his result. Mr. Fitzgerald of Dublin has examined the question mathematically and has shown that Maxwell's theory would have enabled Dr. Kerr's result to be predicted. Another requirement of the theory is that bodies which are transparent to light must be insulators or non-conductors of electricity, and that conductors of electricity are necessarily opaque to light. Simple observation amply confirms this. Metals are the best conductors and are the most opaque bodies known. Insulators such as glass and crystals are transparent whenever they are sufficiently homogeneous. And the very remarkable researches of Professor Graham Bell in the last few months have shown that even ebonite, one of the most opaque insulators to ordinary vision, is certainly transparent to some kinds of radiation, and transparent to no small degree. A further consequence of the theory is that the velocity of light in a transparent medium will be affected by its electrical strain constant. In other words, that its refractive index will bear some close but not yet quite ascertained relation to its specific inductive capacity. Experiment has partially confirmed this, but the confirmation is as yet very incomplete. But there are a number of results not predicted by theory, and whose connection with the theory is not clearly made out. We have the fact that light falling on the platinum electrode of a voltammeter generates a current, first observed, I think, by Sir W.K. Grove. At any rate, it is mentioned in his correlation of forces, extended by Becquerel and Robert Sabine to other substances, and now being extended to fluorescent and other bodies by Professor Minchin. And finally, for I must be brief, we have the remarkable action of light on selenium. This fact was discovered accidentally by an assistant in the laboratory of Mr. Willoughby Smith, who noticed that a piece of selenium conducted electricity very much better when light was falling upon it than when it was in the dark. The light of a candle is sufficient and instantaneously brings down the resistance to something like 1/5 of its original value. This is the phenomenon which, as you know, has been utilized by Professor Graham Bell in that most ingenious and striking invention, the photophone. I have now trespassed long enough upon your patience, but I must just allude to what may very likely be the next striking popular discovery, and that is the transmission of light by electricity. I mean, the transmission of such things as views and pictures by means of the electric wire. It has not yet been done, but it seems already theoretically possible, and it may very soon be practically accomplished. The collation between electricity and light, after Hertz, Substance of a Lecture by Professor Oliver Lodge, Ashmolean Society, Oxford, June 3, 1889. For now well nigh a century, we have had a wave theory of light, and a wave theory of light is certainly real. It is directly demonstrable that light consists of waves of some kind or other, and that these waves travel at a certain well-known velocity, 7 times the circumference of the Earth per second, taking 8 minutes on the journey from the Sun to the Earth. This propagation in time of an undulatory disturbance necessarily involves a medium. If waves setting out from the Sun exist in space 8 minutes before striking our eyes, there must necessarily be in space some medium in which they exist and which conveys them. Waves we cannot have unless they be waves in something. based on a report in the London Electrician September 6, 1889. No ordinary medium is competent to transmit waves at anything like the speed of light. Hence, the luminiferous medium must be a special kind of substance, and it is called the ether. The luminiferous ether it used to be called because the conveyance of light was all it was then known to be capable of. But now that it is known to do a variety of other things also, the qualifying adjective may be dropped. Wave motion in ether light certainly is, but what does one mean by the term wave? The popular notion is, I suppose, of something heaving up and down, or perhaps of something breaking on the shore in which it is possible to bathe. But if you ask a mathematician what he means by a wave, he will probably reply that the simplest wave is hash equals asin P10x, and he might possibly refuse to give any other answer. And in refusing to give any other answer than this, or its equivalent in ordinary words, he is entirely justified. That is what is meant by the term wave, and nothing less general won't be all-inclusive. Translated into ordinary English, the phrase signifies a disturbance periodic both in space and time. Anything thus doubly periodic is a wave, and all waves, whether in air as sound waves or in ether as light waves, or on the surface of water as ocean waves, are comprehended in the definition. What properties are essential to a medium capable of transmitting wave motion? Roughly, we may say two: elasticity and inertia. Elasticity in some form or some equivalent of it in order to be able to store up energy and affect recoil. Inertia in order to enable the disturbed substance to overshoot the mark and oscillate beyond its place of equilibrium to and fro. Any medium possessing these two properties can transmit waves, and unless a medium possesses these properties in some form or other, or some equivalent for them, it may be said with moderate security to be incompetent to transmit waves. But if we make this latter statement, one must be prepared to extend to the terms elasticity and inertia their very largest and broadest signification, so as to include any possible kind of restoring force and any possible kind of persistence of motion, respectively. These matters may be illustrated in many ways, but perhaps a simple loaded lath or spring in a vise will serve well enough. Pull aside one end, and its elasticity tends to make it recoil, let it go, and its inertia causes it to overshoot its normal position. Both causes together cause it to swing to and fro till its energy is exhausted. A regular series of such springs at equal intervals in space, set going at regular intervals of time, one after the other, gives you at once a wave motion and appearance which the most casual observer must recognize as such. A series of pendulums will do just as well. Any wave-transmitting medium must similarly possess some form of elasticity and of inertia. But now proceed to ask, what is this ether, which in the case of light is thus vibrating? What corresponds to the elastic displacement and recoil of the spring or pendulum? What corresponds to the inertia whereby it overshoots its mark? Do we know these properties in the ether in any other way? The answer given first by Clerk Maxwell and now reiterated and insisted on by experiments performed in every important laboratory in the world is the elastic displacement corresponds to electrostatic charge, roughly speaking, to electricity. The inertia corresponds to magnetism. This is the basis of the modern electromagnetic theory of light. Now let me illustrate electrically how this can be. The old and familiar operation of charging a Leyden jar, the storing up of energy in a strained dielectric, any electrostatic charging whatever, is quite analogous to the drawing aside of our flexible spring. It is making use of the elasticity of the ether to produce a tendency to recoil. Letting go the spring is analogous to permitting a discharge of the jar, permitting the strained dielectric to recover itself, the electrostatic disturbance to subside. In nearly all the experiments of electrostatics, ethereal elasticity is manifest. Next, consider inertia. How would one illustrate the fact that water, for instance, possesses inertia, the power of persisting in motion against obstacles, the power of possessing kinetic energy? The most direct way would be to take a stream of water and try suddenly to stop it. Open a water tap freely and then suddenly shut it. The impetus or momentum of the stopped water makes itself manifest by a violent shock to the pipe, with which everybody must be familiar. The momentum of water is utilized by engineers in the DEC water ram. A precisely analogous experiment in electricity is what Faraday called the extra current. Send a current through a coil of wire around a piece of iron, or take any other arrangement for developing powerful magnetism, and then suddenly stop the current by breaking the circuit. A violent flash occurs if the stoppage is sudden enough, a flash which means the bursting of the insulating air partition by the accumulated electromagnetic momentum. Briefly, we may say that nearly all electromagnetic experiments illustrate the fact of ethereal inertia. Now return to consider what happens when a charged conductor, say a Leyden jar, is discharged. The recoil of the strained dielectric causes a current. The inertia of this current causes it to overshoot the mark, and for an instant the charge of the jar is reversed. The current now flows backwards and charges the jar up as at first. Again flows the current and so on, discharging and charging the jar with rapid oscillations until the energy is all dissipated into heat. The operation is precisely analogous to the release of a strained spring or to the plucking of a stretched string, but the discharging body, thus thrown into strong electrical vibration, is embedded in the all-pervading ether. And we have just seen that the ether possesses the two properties requisite for the generation and transmission of waves, viz. Elasticity and inertia or density. Hence, just as a tuning fork vibrating in air excites aerial waves or sound, so a discharging light jar in ether excites ethereal waves or light. Ethereal waves can therefore be actually produced by direct electrical means. I discharge here a jar, and the room is for an instant filled with light. With light, I say, though you can see nothing, you can see and hear the spark indeed. But that is a mere secondary disturbance we can for the present ignore. I do not mean any secondary disturbance. I mean the true ethereal waves emitted by the electric oscillation going on in the neighborhood of this recoiling dielectric. You pull aside the prong of a tuning fork and let it go. Vibration follows and sound is produced. You charge a Leyden jar and let it discharge. Vibration follows and light is excited. It is light just as good as any other light. It travels at the same pace. It is reflected and refracted according to the same laws. Every experiment known to optics can be performed with this ethereal radiation electrically produced, and yet you cannot see it. Why not? For no fault of the light, the fault, if there be a fault, is in the eye. The retina is incompetent to respond to these vibrations. They are too slow. The vibrations set up when this large jar is discharged are from 100,000 to 1,000,000 per second, but that is too slow for the retina. It responds only to vibrations between 4,000 billions and 7,000 billions per second. The vibrations are too quick for the ear, which responds only to vibrations between 40 and 40 per second. Between the highest audible and the lowest visible vibrations, there has been hitherto a great gap, which these electric oscillations go far to fill up. There has been a great gap simply because we have no intermediate sense organ to detect rates of vibration between 40 and 4,000 per second. It was, therefore, an unexplored territory. Waves have been there all the time in any quantity, but we have not thought about them nor attended to them. It happens that I have myself succeeded in getting electric oscillations so slow as to be audible. The lowest I have got at present are 125 per second, and for some way above this, the sparks emit a musical note. But no one has yet succeeded in directly making electric oscillations which are visible, though indirectly everyone does it by lighting a candle. Here, however, is an electric oscillator which vibrates 300 million times a second and emits ethereal waves a yard long. The whole range of vibrations between musical tones and some 1,000 millions per second is now filled up. These electromagnetic waves have long been known on the side of theory, but interest in them has been immensely quickened by the discovery of a receiver or detector for them. The great though simple discovery by Hertz of the electric eye, as Sir W. Thomson calls it, makes experiments on these waves for the first time possible, or even easy. We have now a sort of artificial sense organ for their appreciation, an electric arrangement which can virtually see these intermediate rates of vibration. The Hertz receiver is the simplest thing in the world, nothing but a bit of wire or a pair of bits of wire, adjusted so that when immersed in strong electric radiation, they give minute sparks across a microscopic air gap. The receiver I have here is adapted for the yard-long waves emitted from this small oscillator. But for the far longer waves emitted by a discharging Leyden jar, an excellent receiver is a gilt wallpaper or other interrupted metallic surface. The waves falling upon the metallic surface are reflected, and in the act of reflection excite electric currents, which cause sparks. Similarly, gigantic solar waves may produce aurorae, and minute waves from a candle do electrically disturb the retina. The smaller waves are, however, far the most interesting and the most tractable to ordinary optical experiments. From a small oscillator, which may be a couple of small cylinders kept sparking into each other, end to end by an induction coil, waves are emitted on which all manner of optical experiments can be performed. They can be reflected by plain sheets of metal, concentrated by parabolic reflectors, refracted by prisms, concentrated by lenses. I have at the college a large lens of pitch, weighing over 3 cW2, for concentrating them to a focus. They can be made to show the phenomenon of interference, and thus have their wavelengths accurately measured. They are stopped by all conductors and transmitted by all insulators. Metals are opaque, but even imperfect insulators, such as wood or stone, are strikingly transparent, and waves may be received in one room from a source in another, the door between the two being shut. The real nature of metallic opacity and of transparency has long been clear in Maxwell's theory of light, and these electrically produced waves only illustrate and bring home the well-known facts. The experiments of Hertz are, in fact, the apotheosis of that theory. Thus, then, in every way, Maxwell's brilliant perception of the real nature of light is abundantly justified. And for the first time, we have a true theory of light, no longer based upon analogy with sound, nor upon a hypothetical jelly or elastic solid. Light is an electromagnetic disturbance of the ether. Optics is a branch of electricity. Outstanding problems in optics are being rapidly solved now that we have the means of definitely exciting light with a full perception of what we are doing and of the precise mode of its vibration. It remains to find out how to shorten down the waves, to hurry up the vibration until the light becomes visible. Nothing is wanted but quicker modes of vibration. Smaller oscillators must be used, very much smaller. Oscillators not much bigger than molecules. In all probability, one may almost say certainly, ordinary light is the result of electric oscillation in the molecules of hot bodies, or sometimes of bodies not hot, as in the phenomenon of phosphorescence. The direct generation of visible light by electric means. So soon as we have learned how to attain the necessary frequency of vibration, will have most important practical consequences. For consider our present methods of making artificial light. They are both wasteful and ineffective. We want a certain range of oscillation between 7,000 and 4,000 billion vibrations per second. No other is useful to us because no other has any effect upon our retina. But we do not know how to produce vibrations of this rate. We can produce a definite vibration of 1 or 200 or 1,000 per second. In other words, we can excite a pure tone of definite pitch, and we can command any desired range of such tones continuously by means of bellows and a keyboard. We can also, though the fact is less well known, excite momentarily definite ethereal vibrations of some millions per second, as I have explained. But we do not at present seem to know how to maintain this rate quite continuously. To get much faster rates of vibration than this, we have to fall back upon atoms. We know how to make atoms vibrate. It is done by what we call heating the substance. And if we could deal with individual atoms unhampered by others, it is possible that we might get a pure and simple mode of vibration from them. It is possible, but unlikely, for atoms, even when isolated, have a multitude of modes of vibration special to themselves, of which only a few are of practical use to us. And we do not know how to excite some without also the others. However, we do not at present even deal with individual atoms. We treat them crowded together in a compact mass, so that their modes of vibration are really infinite. We take a lump of matter, say a carbon filament or a piece of quicklime, and by raising its temperature, we impress upon its atoms higher and higher modes of vibration. not transmuting the lower into the higher, but superposing the higher upon the lower, until at length we get such rates of vibration as our retina is constructed for, and we are satisfied. But how wasteful and indirect and empirical is the process? We want a small range of rapid vibrations, and we know no better than to make the whole series leading up to them. It is as though in order to sound some little shrill octave of pipes in an organ, we are obliged to depress every key and every pedal, and to blow a young hurricane. I have purposely selected as examples the more perfect methods of obtaining artificial light, wherein the waste radiation is only useless and not noxious. But the old-fashioned plan was cruder even than this. It consisted simply in setting something burning whereby not the fuel but the air was consumed, whereby also a most powerful radiation was produced in the waste waves of which we were content to sit stewing, for the sake of the minute, almost infinitesimal, fraction of it which enabled us to see. Everyone knows now, however, that combustion is not a pleasant or healthy mode of obtaining light. But everybody does not realize that neither is incandescence a satisfactory and unwasteful method, which is likely to be practiced for more than a few decades or perhaps a century. Look at the furnaces and boilers of a great steam engine driving a group of dynamos and estimate the energy expended, and then look at the incandescent filaments of the lamps excited by them, and estimate how much of their radiated energy is of real service to the eye. It will be as the energy of a pitch pipe to an entire orchestra. It is not too much to say that a boy turning a handle could, if his energy were properly directed, produce quite as much real light as is produced by all this massive mechanism. And might perhaps be something contrary to the laws of nature in thus hoping to get and utilize some specific kind of radiation without the rest. But Lord Ely has shown in a short communication to the British Association at York that it is not so, and that therefore we have a right to try to do it. We do not yet know how, it is true, but it is one of the things we have got to learn. Anyone looking at a common glowworm must be struck with the fact that not by ordinary combustion, nor yet on the steam engine and dynamo principle, is that easy light produced. Very little waste radiation is there from phosphorescent things in general. Light of the kind able to affect the retina is directly emitted, and for even a large supply of this, a modicum of energy suffices. Solar radiation consists of waves of all sizes, it is true, but then solar radiation has innumerable things to do besides making things visible. The whole of its energy is useful. In artificial lighting, nothing but light is desired. When heat is wanted, it is best obtained separately by combustion. And so soon as we clearly recognize that light is an electrical vibration, so soon shall we begin to beat about for some mode of exciting and maintaining an electrical vibration of any required degree of rapidity. When this has been accomplished, the problem of artificial lighting will have been solved. Chapter 26. Appendix B. High Tension, Electricity and Modern Views of Electric Currents. Prophet Henry on high tension, electricity being confined to the surface of conducting bodies with special reference to the proper construction of Le Chitning E-Eats, extracted from the L Journal of the Telegraph. 1. 1877. Washington, March 11th, 1876. Dear Sir, in answer to your letter of the 7th inst., I have to say that the discrepancy which exists as to the question whether electricity passes at the surface or through the whole capacity of the rod has arisen principally from experiments on galvanic electricity, which, having little or no repulsive energy, passes through the whole substance of the rod, and also from experiments in which a very large quantity of frictional electricity is transmitted through a small wire. In this case, the metal is resolved into its elements and reduced to an impalpable powder. In the case, however, of the transmission of atmospheric electricity through a rod of sufficient size to transmit the discharge free, there can be no doubt that it tends to pass at the surface, the thickness of the stratum of electricity varying with the diameter of the rod and the amount and the intensity of the charge. To test this by actual experiment, I made the following arrangement. Through a gun barrel about 2 feet in length, a copper wire was passed, the ends projecting. The middle of the wire in the barrel was coiled into the form of a magnetizing spiral, and the ends of the gun barrel were closed with plugs of tinfoil, so as to make a perfect metallic connection between the wire and the barrel. On the outside of the barrel, another magnetizing spiral was placed, the whole arrangement being shown in the sketch. A powerful charge was now sent through the copper wire from a Leyden jar of about 2 gallons capacity. The needle within the barrel showed not the least sign of magnetism, while the one on the outside was strongly magnetic. From this experiment, I conclude that a gas pipe can convey an ordinary charge of electricity from the clouds, as well as a solid rod of the same diameter. The repulsive energy of the electrical discharge at right angles to the axis remains of the same intensity as in the case of a statical charge. This I have shown to be the case by drawing sparks of considerable intensity from a conductor, one end of which was connected with the ground, while sparks were thrown on the other end from a large prime conductor. This spark is of a peculiar character, for though it gives a pungent shock and sets fire to combustible substances, such as an electrical pistol, it does not affect a sensitive gold leaf electrometer. The fact is, it consists of 2 sparks, the one negative and the other positive. The rod during the transmission of the electricity through it is charged plus at the upper end, and immediately in advance of this point, it is charged by induction. And the electricity passes through it in the discharge in the form of a series of plus and waves. Yours very truly, Joseph Henry, Sec. Smithsonian Inst., Professor E. C. Kedzie, Lansing, Michigan, Washington, April 15, 1876. Dear Sir, your letter was received by due course of mail, but a press of business connected with the preparation of the annual keyport for 1875, and the Lighthouse Board has prevented an earlier reply. I have now to say that, as far as I know, I'm the only person who has made a special study of the conduction of frictional electricity in regard to lightning rod. It has long been established by Coulomb and others that the electricity of a charged conductor exists in a thin stratum at the surface, and this is a necessary consequence of the repulsion of electricity for itself, every particle being repelled from every other as far as possible. From this, it was hastily assumed that electricity in motion also moves at the surface. But this was an inference without physical proof until I commenced the investigate. I found from a series of experiments that frictional electricity, that is, electricity of repulsive energy, such as that from the clouds, does pass at the surface. But that galvanic electricity, the kind to which Faraday, Daniel de la Rive, and others refer, passes through the whole capacity of the conductor. This latter fact, however, was previously established by others. I further found that whenever a charge of electricity was thrown on a rod explosively, however well connected the rod was with the earth, it gave off sparks in the course of its length sufficient to fire an electric pistol and light flocculent substances. I also found that, in sending a powerful discharge from a battery of 9 jars through a wide plate, no electricity passed along the middle of the plate, but that it was accumulated in its passage at the edges. From all my study of this subject, I do not hesitate to say that the plan I have given of lightning rods is the true one, and that a tube of a sufficient degree of thickness serves to conduct the electricity as well as a solid mass, provided the thickness is sufficient to give free conduction. A very heavy charge sent through a wire frequently deflagrates it, but no discharge from the clouds, of which I have any knowledge, has ever sufficed to deflagrate a gas pipe of an inch in diameter. The plan of increasing the surface of a rod by converting the metal into a ribbon is objectionable. It tends to increase the power of the lateral discharge and gives no increase of conducting power. Another fallacy is much insisted on, viz. The better conduction of copper than iron. It is true that copper is a better conductor of galvanic electricity, which pervades the whole mass. But in regard to frictional electricity, the difference in conducting capacity is too small to be of any importance. Iron is sufficiently good in regard to conduction and withstands deflagration, better than copper. Besides this, it is much cheaper. Yours truly, Joseph Henry, Professor R. C. Kedzie. On Modern Views with Respect to the Nature of Electric Currents. Substance of a lecture by Professor H. A. Owland, American Institute of Electrical Engineers, May 22nd, 1880. How great, then, the difference between a current of water and a current of electricity. The action of the former is confined to the interior of the tube, while that of the latter extends to great distances on all sides, the whole of the space being agitated by the formation of an electric current in any part. To show this agitation, I have here two large frames with coils of wire around them. They hang face to face, about 6 feet apart. Through one I discharge this Leyden jar, and immediately you see a spark and a break in the wire of the other coil, and yet there is no apparent connection between the two. I can carry the coils 50 feet or more apart, and yet by suitable means I can observe the disturbances due to the current in the first coil. The question is forced upon us as to how this action takes place. How is it possible to transmit so much power to such a distance across apparently unoccupied space? According to our modern theories of physics, there must be some medium engaged in this transmission. We know that it is not the air, because the same effects take place in a vacuum, and therefore we must fall back on that medium which transmits light, and which we have named the ether, that medium which is supposed to extend unaltered throughout the whole of space, whose existence is very certain, but whose properties we have yet but vaguely conceived. I cannot in the course of 1 short hour give even an idea of the process by which the minds of physicists have been led to this conclusion, or the means by which we have finally completely identified the ether which transmits light with the medium which transmits electrical and magnetic disturbances. The great genius who first identified the two is Maxwell, whose electromagnetic theory of light is the center around which much scientific thought is today revolving, and which we regard as one of the greatest steps by which we advance nearer to the understanding of matter and its laws. It is this great discovery of Maxwell which allows me to attempt to explain to you the wonderful events which happen everywhere in space when one establishes an electric current in any other portion. In the first place, we discover that the disturbance does not take place in all portions of space at once, but proceeds outward from the center of the disturbance with a velocity exactly equal to the velocity of light. So that when I touch these wires together so as to complete the circuit of yonder battery, I start a wave of ethereal disturbance, which passes outward with a velocity of 185 miles per second, and continues to pass outwards forever, or until it reaches the bounds of the universe. And yet none of our senses informs us of what has taken place unless sharpened by the use of suitable instruments. Thus, in the case of these two coils of wire, suspended near each other, when the wave from the primary disturbance reaches the second coil, we perceive the disturbance by means of the spark formed at the break in the coil. Should I move the coils farther apart, the spark in the second coil would be somewhat delayed, but the distance of 185 miles would be necessary before this delay could amount to as much as 1 second. Hence, the effects we observe on the Earth take place so nearly instantaneously that the interval of time is very difficult to measure, amounting in the present case to only t-th of a second. It is impossible for me to prove the existence of this interval, so infinitesimal is it, but I can at least show you that waves have something to do with the action observed. For instance, I have here 2 tuning forks mounted on sounding boxes and tuned to exact unison. I sound one and then stop its vibrations with my hand. Instantly you hear that the other is in vibration caused by the waves of sound in the air between the two. When, however, I destroy the unison by fixing this piece of wax on one of the forks, the action ceases. Now, this combination of a coil of wire and a Leyden jar forms a vibrating system of electricity, and its time of vibration is about 10 times a second. Here is another combination of coil and jar, the same as the first, and therefore its time of vibration is the same. You see how well the experiment works, because the two are in unison. But let me take away this second Leyden jar, thus destroying the unison, and you see that the sparks instantly cease. Placing it, the sparks reappear. Adding another on one side, they disappear again, only to reappear when the system is made symmetrical, by placing 2 on each side. This experiment and that of the tuning forks have an exact analogy to one another. In each, we have 2 vibrating systems connected by a medium capable of transmitting vibrations, and they both come under the head of what we know as sympathetic vibrations. In the one case, we have two mechanical tuning forks connected by the air. In the other, two pieces of apparatus, which we might call electrical tuning forks, connected by the ether. The vibrations in one case can be seen by the eye or heard by the ear, but in the other case, they can only be perceived when we destroy them by making them produce a spark. The fact that we are able to increase the effect by proper tuning demonstrates that vibrations are concerned in the phenomenon. This can, however, be separately demonstrated by examining the spark by means of a revolving mirror. When we find that it is made up of many successive sparks corresponding to the successive backward and forward movements of the current. In the case of a charged Leyden jar whose inner and outer coatings have been suddenly joined by a wire, the electricity flows back and forth along the wire until all the energy originally stored up in the jar has expended itself in heating the wire or the air where the spark takes place, and in generating waves of disturbance in the ether which move outward into space with the velocity of light. These ethereal waves we have demonstrated by letting them fall on this coil of wire, causing the electrical disturbance to manifest itself by electric sparks. I have here another more powerful arrangement for producing electromagnetic waves of very long wavelength, each one being about 500 miles long. It consists of a coil within which is a bundle of iron wires. On passing a powerful alternating current through the coil, the iron wires are rapidly magnetized and demagnetized, and send forth into space a system of electromagnetic waves at the rate of 360 in a second. Here also, I have another piece of apparatus for sending out the same kind of electromagnetic waves, and on applying a match, we start it also into action. But the last apparatus is tuned to so high a pitch that the waves are only due inson long, and 55,000 are given out in 1 second. These short waves are known by the name of light and radiant heat, though the name radiation is more exact. Placing any body near the lamp so that the radiation can fall on it, we observe that when the body absorbs the rays, it is heated by it. Is it not possible for us to get some substance to absorb the long or electromagnetic waves of disturbance, and so obtain a heating effect when I have here such a substance in the shape of a sheet of copper, which I fasten on the face of a thermopile, and I hold it where these waves are strongest? As I have anticipated, great heat is generated by their absorption, and soon the plate of copper becomes very warm, as we see by this thermometer, by feeling it with the hand, or even by the steam from water thrown upon it. In this experiment, the copper had not touched the coil or the iron wire core, although if it did, they are very much cooler than itself. The heat has been produced by the absorption of the waves, in the same way as a blackened body absorbs the rays of shorter wavelength from the lamp. In these experiments, so far, the wave-like nature of the disturbance has not been proved. We have caused electric sparks and have heated the copper plate across an interval of space, but have not in either of these cases proved experimentally the progressive nature of the disturbance. A ready means of experimenting on the waves, obtaining their wavelength, and showing their interferences has hitherto been wanting. This deficiency has been recently supplied by Professor Hertz of Karlsruhe. I scarcely know how to present this subject to a non-technical audience and make it clear how a coil of wire with a break in it can be used to measure the velocity and length of ethereal waves. However, I can but try. If the waves moved very slowly, we could readily measure the time the first coil took to affect the second, and show that this time was longer as the distance was greater. But it is absolutely inappreciable by any of our instruments, and another method must be found. To obtain the wavelength, Professor Hertz used several methods, but that by the formation of stationary waves is the most easily grasped. I hold in my hand one end of a spiral spring, which makes a heavy and flexible rope. As I send a wave down it, you see that it is reflected at the farther end, and returns again to my hand. If, however, I send a succession of waves down the rope, the reflected waves interfere with the direct ones, and divide the rope into a succession of nodes and loops, which you now observed. So a series of sound waves striking on a wall forms a system of stationary waves in front of the wall. Indeed, we can use any waves for this purpose, even ethereal waves. With this in view, Professor Hertz established his apparatus in front of a reflecting wall, and observe the nodes and loops by the sparks produced in a ring of wire, somewhat resembling the coil I've been using, but much smaller. It is impossible for me to repeat this experiment before you, as it is a very delicate one, and the sparks produced are almost microscopic. Indeed, I should have to erect an entirely different apparatus, as the waves from the one before me are nearly a quarter-mile long. To produce shorter waves, we must use apparatus very much smaller, tuned, as it were, to a higher pitch, so that several stationary waves, or nodes and loops, of a few yards long could be obtained in the space of this room. The testing coil would then be moved to different parts of the room, and the nodes would be indicated by the disappearance of the sparks, and the loops by the greater brightness of them. The presence of stationary waves would thus be proved, and their half-wave length found from the distance from node to node. For stationary waves can always be considered as produced by the interference of two waves advancing in opposite directions. The closing of a battery circuit, then, and the establishment of a current of electricity in a wire is a very different process from the formation of a current of water in a pipe. Though after the first shock, the laws of the flow of the two are very much alike. Furthermore, the medium around the current of electricity has very strange properties, showing that it is accompanied by a disturbance throughout space. The wire is but the core of the disturbance, which latter extends indefinitely in all directions. One of the strangest things about it is that we can calculate with perfect exactness the velocity of the wave propagation and the amount of the disturbance at every point and at any instant of time. But as yet, we cannot conceive of the details of the mechanism which is concerned in the propagation of an electric current. In this respect, our subject resembles all other branches of physics in the partial knowledge we have of it. We know that light is the undulation of the luminiferous ether, and yet the constitution of the latter is unknown. We know that the atoms of matter can vibrate with purer tones than the most perfect piano, and yet we cannot even conceive of their constitution. We know that the sun attracts the planets with a force whose law is known. And yet, we fail to picture to ourselves the process by which it takes our Earth within its grasp at the distance of many millions of miles and prevents it from departing forever from its life-giving rays. Science is full of this half-knowledge. So far, we have considered the case of alternating electric currents in a wire connecting the inner and outer coatings of a Leyden jar. The invention of the telephone, by which sound is carried from one point to another by means of electrical waves, has forced into prominence the subject of these waves. Furthermore, the use of alternating currents for electric lighting brings into play the same phenomenon. Here, again, the difference between a current of water and a current of electricity is very marked. A sound wave traversing the water in the tube produces a to and fro current of water at any given point. So in the electrical vibration along a wire, the electricity moves to and fro along it in a manner somewhat similar to the water. But with this difference, the disturbance from the water motion is confined to the tube, and the oscillation of the water is greatest in the center of the tube, while in the case of the electric current, the ether around the wire is disturbed. And the oscillation of the current is greatest at the surface of the wire and least in its center. The oscillations in the water take place in the tube without reference to the matter outside the tube. Whereas the electric oscillations in the wire are entirely dependent on the surrounding space, and the velocity of the propagation is nearly independent of the nature of the wire, provided it is a good conductor. We have then, in the case of electrical waves along a wire, a disturbance outside the wire and a current within it, and the equations of Maxwell allow us to calculate these with perfect accuracy and give all the laws with respect to them. We thus find that the velocity of propagation of the waves along a wire, hung far away from other bodies and made of good conducting material, is that of light, or 185 miles per second. But when it is hung near any conducting matter like the Earth, or enclosed in a cable and sunk into the sea, the velocity becomes much less. When hung in space, away from other bodies, it forms, as it were, the core of the system of waves in the ether, the amplitude of the disturbance becoming less and less as we move away from the wire. But the most curious fact is that the electric current penetrates only a short distance into the wire, being mostly confined to the surface, especially where the number of oscillations per second is very great. The electrical waves at the surface of a conductor are thus, in some respects, very similar to the waves on the surface of water. The greatest motion in the latter case is at the surface, while it diminishes as we pass downwards and soon becomes inappreciable. Furthermore, the depth to which the disturbance penetrates into the water increases with increase of the length of the wave, being confined to very near the surface for very short waves. So the disturbance in the copper penetrates deeper as the waves and the time of oscillation are longer, and the disturbance is more nearly confined to the surface as the waves become shorter. There are very many practical applications of these theoretical results for electric currents. The most obvious one is to the case of conductors for the alternating currents used in producing the electric light. We find that when these are larger than about half an inch diameter, they should be replaced by a number of conductors less than half an inch diameter, or by strips about a quarter of an inch thick and of any convenient width. Professor Oliver Lodge has recently drawn attention to another application of these results, that is, to lightning rods. Almost since the time of Franklin, there have been those who advocated the making of lightning rods, hollow, in order to increase the surface for a given amount of copper. We now know that these persons had no reason for their belief, as they simply drew the inference that electricity at rest is on the surface. Neither were the advocates of the solid rods quite correct, for they reasoned that electricity in a state of steady flow occupies the whole area of the conductor equally. The true theory, we now know, indicates that neither party was entirely correct, and that the surface is a very important factor in the case of a current of electricity so sudden as that from a lightning discharge. But increase of surface can best be obtained by multiplying the number of conductors, rather than making them flat or hollow. Theory indicates that the current penetrates only 1/10 the distance into iron that it does into copper. As the iron has 7 times the resistance of copper, we should need 70 times the surface of iron that we should of copper. Hence I prefer copper wire about a quarter of an inch diameter, and nailed directly to the house without insulators, and passing down the 4 corners, around the eaves and over the roof, for giving protection from lightning in all cases where a metal roof and metal downspouts do not accomplish the same purpose. Whether the discharge of lightning is oscillatory or not does not enter into the question, provided it is only sufficiently sudden. I have recently solved the mathematical problem of the electric oscillations along a perfectly conducting wire joint burning, and dropped the bar. His fingers were badly blistered, though on examining the bar a few seconds afterwards, it was found to be quite cold. This proved that the action lay at the surface, and had not time to sensibly penetrate the substance of the bar. There were 2 little hollows burned out of the metal at the points where it touched the dynamo terminals. JJF in GU infinite and perfectly conducting planes parallel to each other, and find that there is no definite time of oscillation, but that the system is capable of vibrating in any time in which it is originally started. The case of lightning between a cloud of limited extent and the earth along a path through the air of great resistance is a very different problem. Both the cloud and the path of the electricity are poor conductors, which tends to lengthen the time. If I were called on to estimate as nearly as possible what took place in a flash of lightning, I would say that I did not believe that the discharge was always oscillating, but more often consisted of 1 or more streams of electricity at intervals of a small fraction of a second, each one continuing for not less than Tetsuo second. An oscillating current with 100 zero reversals per second would penetrate about UA inch into copper and GA inch into iron. The depth for copper would constitute a considerable proportion of a wire J inch diameter, and as there are other considerations to be taken into account, I believe it is scarcely worthwhile making tubes or flat strips for such small sizes. It is almost impossible to draw proper conclusions from experiments on this subject in the laboratory, such as those of Professor Oliver Lodge. The time of oscillation of the current in most pieces of laboratory apparatus is so very small, being often the degrees a second, that entirely wrong inferences may be drawn from them. As the size of the apparatus increases, the time of oscillation increases in the same proportion and changes the whole aspect of the case. I have given rho degrees a second as the shortest time a lightning flash could probably occupy. I strongly suspect it is often much greater, and thus departs even further from the laboratory experiments of Professor Lodge, who has, however, done very much towards drawing attention to this matter and showing the importance of surface in this case. All shapes of the rod with equal surface are not, however, equally efficient. Thus, the inside surface of a tube does not count at all. Neither do the corrugations on a rod count for the full value of the surface they expose, for the current is not distributed uniformly over the surface. But I have recently proved that rapidly alternating currents are distributed over the surface of very good conductors in the same manner as electricity at rest would be distributed over them, so that the exterior angles and corners possess much more than their share of the current, and corrugations on the wire concentrate the current on the outer angles and diminish it in the hollows. Even a flat strip has more current on the edges than in the center. For these reasons, shape, as well as extent of surface, must be taken into account, and strips have not always an advantage over wires for quick discharge. The fact that the lightning rod is not melted on being struck by lightning is not now considered as any proof that it has done its work properly. It must, as it were, seize upon the discharge and offer it an easier passage to the earth than any other. Such sudden currents of electricity we have seen to obey very different laws from continuous ones, and their tendency to stick to a conductor and not fly off to other objects depends not only on having them of small resistance, but also on having what we call the self-induction as small as possible. This latter can be diminished by having the lightning rod spread sideways as much as possible, either by rolling it into strips, or better, by making a network of rods over the roof with several connections to the earth at the corners, as I have before described. Thus we see that the theory of lightning rods, which appeared so simple in the time of Franklin, is today a very complicated one, and requires for its solution a very complete knowledge of the dynamics of electric currents. In the light of our present knowledge, the frequent failure of the old system of rods is no mystery. For I doubt if there are 100 buildings in the country properly protected from lightning. With our modern advances, perfect protection might be guaranteed in all cases if expense were no object. We have now considered the case of oscillations of electricity in a few cases, and can turn to that of steady currents. The closing of an electric circuit sends ethereal waves throughout space, but after the first shock, the current flows steadily without producing any more waves. However, the properties of the space around the wire have been permanently altered, as we have already seen. Let us now study these properties more in detail. I have before me a wire in which I can produce a powerful current of electricity. And we have seen that the space around it has been so altered that a delicately suspended magnetic needle cannot remain quiet in all positions, but stretches itself at right angles to the wire, the North Pole tending to revolve around it in one direction and the South Pole in the other. This is a very old experiment, but we now regard it as evidence that the properties of the space around the wire have been altered rather than that the wire acts on the magnet from a distance. Put now a plate of glass around the wire, the latter being vertical and the former with its plane horizontal, and pass a powerful current through the wire. On now, sprinkling iron filings on the plate, they arrange themselves in circles around the wire, and thus point out to us the celebrated lines of magnetic force of Faraday. Using two wires with currents in the same direction, we get these other curves, and testing the forces acting on the wire, we find that they are trying to move towards each other. Again, pass the currents in the opposite directions, and we get these other curves, and the currents repel each other. If we assume that the lines of force are like rubber bands, which tend to shorten in the direction of their length and repel each other sideways, Faraday and Maxwell have shown that all magnetic attractions and repulsions are explained. The property which the presence of the electric current has conferred on the ether is then one by which it tends to shorten in one direction and spread out in the other two directions. We have thus done away with action at a distance and have accounted for magnetic attraction by a change in the intervening medium, as Faraday partly did almost 50 years ago. For this change in the surrounding medium is as much a part of the electric current as anything that goes on within the wire. To illustrate this tension along the lines of force, one have constructed this model, which represents the section of a coil of wire with a bar of iron within it. The rubber bands represent the lines of force which pass around the coil and through the iron bar, as they have an easier passage through the iron than the air. As we draw the bar down and let it go, you see that it is drawn upward and oscillates around its position of equilibrium until friction brings it to rest. Here again, I have a coil of wire with an iron bar within it with one end resting on the floor. As we pass the current and the lines of magnetic force form around the coil and pass through the iron, it is lifted upwards. Although it weighs 24 pounds and oscillates around its position of equilibrium, exactly the same as though it were sustained by rubber bands, as in the model. The rubber bands in this case are invisible to our eye, but our mental vision pictures them as lines of magnetic force in the ether, drawing the bar upward by their contractile force. This contractile force is no small quantity, as it may amount, in some cases, to 1 or even 200 pounds to the square inch, and thus rivals the greatest pressure which we use in our steam engine. Thus, the ether is today a much more important factor in science than the air we breathe. We are constantly surrounded by the two, and the presence of the air is manifest to us all. We feel it, we hear by its aid, and we even see it under favorable circumstances, and the velocity of its motion, as well as the amount of moisture it carries, is a constant topic of conversation. The ether, on the other hand, eludes all our senses, and it is only with imagination, the eye of the mind, that its presence can be perceived. By its aid in conveying the vibrations we call light, we are enabled to see the world around us. And by its other motions, which cause magnetism, the mariner steers his ship through the darkest night when the heavenly bodies are hid from view. When we speak in a telephone, the vibrations of the voice are carried forward to the distant point by waves in the ether, there again to be resolved into the sound waves of the air. When we use the electric light to illuminate our streets, it is the ether which conveys the energy along the wires as well as transmits it to our eye, after it has assumed the form of light. We step upon an electric streetcar and feel it driven forward with the power of many horses. And again, it is the ether whose immense force we have brought under our control and made to serve our purpose, no longer a feeble, uncertain sort of medium, but a mighty power extending throughout all space and binding the whole universe together. Chapter 27. Appendix C. Variations of conductivity under electrical influence. Variations of conductivity under electrical influence. Substance of a paper by Professor E. Bromley of the Catholic University of Paris. The object of this article is to describe the first results obtained in an investigation of the variation or resistance of a large number of conductors under various electrical influences. The substances which, up to the present, have presented the greatest variations in conductivity are the powders or filings of metals. The enormous resistance offered by metal in a state of powder is well known. Indeed, if we take a somewhat long column of very fine metallic powder, the passage of the current is completely stopped. The increase in the electrical conductivity by pressure of powdered conducting substances is also well known and has had various practical applications. The variations of conductivity, however, which occur on subjecting conducting bodies to various electrical influences, have not been previously investigated. The effect of electric sparks. Let us take a circuit comprising a single cell, a galvanometer, and some powdered metal enclosed in an ebonite tube of 1 square centimeter cross-section and a few centimeters long. Close the extremities of the tube with 2 cylindrical copper tubes pressing against the powdered metal and connected to the rest of the circuit. If the powder is sufficiently fine, even a very sensitive galvanometer does not show any evidence of a current passing. The resistance is of the order of millions of ohms, although the same metal melted or under pressure would only offer it, the dimensions being the same. A resistance equal to a fraction of an ohm, there being therefore no current in the circuit. A Leyden jar is discharged at some little distance off, when the abrupt and permanent deflection of the galvanometer needle shows that an immediate and a permanent reduction of the resistance has been caused. The resistance of the metal is no longer to be measured in millions of ohms, but in hundreds. Its conductivity increases with the number and intensity of the some 20 or 30 centimeters from a circuit comprising some metallic filings contained in an ebonite cup. Let us place a hollow brass sphere 15 to 20 centimeters in diameter, insulated by a vertical glass support. The filings offer an enormous resistance, and the galvanometer needle remains at 0. But if we bring an electrified stick of resin near the sphere, a little spark will pass between the stick and the sphere, and immediately the needle of the galvanometer is violently jerked, and then remains permanently deflected. On some fresh filings being placed in the ebonite cup, the resistance of the circuit will again keep the needle at 0. If now the charged brass sphere is touched with the finger, there is a minute discharge, and the galvanometer needle is again deflected. With a few accumulators, the experiment can easily be made without a galvanometer. The circuit consists of the battery, some metallic powder, a platinum wire, and a mercury cup. The resistance of the powder is so high that the interruption of the circuit takes place without any sparking of the mercury cup. If now a Leyden jar is discharged in the neighborhood of the circuit, the powder is rendered conducting. The platinum wire immediately becomes red hot, and a violent spark occurs on breaking the circuit. The influence of the spark decreases as the distance increases, but its influence is observable several meters away from the powder, even with a small Wimshurst machine. Repeating the spark increases the conductivity. In fact, with certain substances, successive sparks produce successive jerks, and a gradually increasing and persistent deflection of the galvanometer needle. Influence of a conductor traversed by condenser discharges. While using the Wimshurst machine, it was noticed that the reduction in the resistance of the filings frequently took place before discharge. This led me to the following experiment. Take a long brass tube, one end of which is close to the circuit containing the metallic powder. Its other end, several meters distant from the circuit, is fairly close to a charged Leyden jar. A spark takes place and the conductor is charged. At the same instant, the conductivity of the metallic powder is greatly increased. The following arrangement, owing to its efficacy, convenience, and regularity of action, was used by me in most of my researches, and I shall briefly call it the A arrangement. The source of electricity is a two-plate Holtz machine driven at from 100 to 400 revolutions. A sensitive substance is introduced into one of the arms of a Wheatstone bridge, or into the circuit of a single Daniell cell at a 11 Lionel of some 10 meters from the Holtz-Spurf QJIJ machine. Between the discharge knobs of the machine and the Wheatstone bridge, and connected to the former, there are two insulated brass tubes, A, running a parallel to one another, 40 centimeters apart. The Leyden jar is usually attached to a Holtz machine, may be dispensed with. The capacity of the long brass tubes, the figure, being in some measure equivalent to them. The knobs were 1 millimeters, 5 millimeters, or 1 millimeters apart. When the plates were rotated, sparks rapidly succeeded each other. Experiments showed that these sparks had no direct effect at a distance of 10 meters. The two tubes are not absolutely necessary. The diminution of resistance is easily produced if only one is employed. And in some cases, indeed, a single conductor is more efficacious. An increase in the speed of the machine increases its action to a marked extent. The sparks at S may be suppressed by drawing the knobs apart, but the conductor will still continue to exert its influence, especially if there is a spark gap anywhere about. Effects of induced currents. The passage of induced currents through a sensitive substance produces similar effects to those described above. In one instance, an induction coil was taken, having two similar wires. The circuit of the secondary wire was closed through a tube containing filings, the galvanometer being also in circuit. Care was taken to ascertain before introducing the filings into the circuit that the currents on make and break gave equal and opposite deflections. Filings were then introduced into the circuit, the primary being made and broken at regular intervals. The following table gives the results obtained in the case of zinc filings, galvanometer throws. First closing, 1 degrees first opening, 18 degrees second, 64 degrees second, 100 degrees third. 146 degrees, third, 140 degrees effects of passing continuous currents of high EMF. If a continuous current of high EMF is employed, it renders a sensitive substance conducting. The phenomenon may be shown in the following manner. A circuit is made up consisting of a battery, a sensitive substance, and a galvanometer. The EMF of the battery is first 1 volt, then 100 volts, then 1 volt. Below, I give the galvanometer deflections obtained with an EMF of 1 volt for 3 different substances before and after the application of the EM of 100 volts. Before application, after application of current. 16, 100, 0, 15, 115, 1 in the case of some measurements taken on a Wheatstone bridge. A prism of aluminium filings interposed between 2 copper electrodes offered a resistance of several million ohms before a high EMF was applied, but only offered a resistance of 350 ohms after the application of this pressure for 1 minute. The time during which the powder should be interposed in the battery circuit should not be too short. Thus, in one instance, the application for 10 seconds of 75 mercury sulfate cells produced no effect, but their application for 60 seconds resulted in the resistance being reduced from several megohms to 2,500 ohms. It should be observed that the phenomenon of suddenly increased conductivity occurs even if the sensitive substance is appendix C not in circuit with a battery at the time it is influenced. Thus, the metallic filings, after having been placed in circuit with a Daniell cell and their high resistance observed, may then be completely insulated and submitted in this condition to the action of a distant spark or of a charged rod or of induced currents. If after this the filings are replaced in their original circuit, the enormous increase in their conductivity is immediately apparent. The conductivity produced by these various methods takes place throughout the whole mass of the metallic filings and in every direction, as the following experiment will show. A vertical ebonite cup containing aluminium powder, the figure, is placed between 2 metal plates A, B, D. Laterally, the powder is in contact with 2 short rods C, D, which pass through the sides of the ebonite cylinder. A and B can be connected to 2 terminals of one of the arms of the Wheatstone bridge, C and D being free, and vice versa, whatever arrangement is adopted. If a battery of 100 cells is joined up for a few seconds with one or the other of the pairs of terminals, the increase in the conductivity is immediately visible in that direction, and is found to exist also in the direction at right angles. Substances in which diminution of resistance has been observed. The substances in which the phenomenon of the sudden increase of conductivity is most easily observed are filings of iron, aluminium, copper, brass, antimony, tellurium, cadmium, zinc, bismuth, and C. The size of the grains and their nature are not the only elements to be considered for grains of lead of the same size, but coming from different quarters. Offer at the same temperature great differences in resistance 20 to 500 ohms. Extremely fine metallic powder, as a rule, offers almost perfect resistance to the passage of a current. But if we take a sufficiently short column and exert a sufficiently great pressure, a point is soon reached when the electrical influence will affect a sudden increase in the conductivity. If variations of conductivity, thus a layer of copper reduced by hydrogen, which does not become conducting under the influence of the electric spark or otherwise, will become so on being submitted to a pressure of 500 grams to the square centimeter 7 IB per square inch. Instead of using pressure, I employed as a conductor in some experiments a very fine coating of powdered copper spread on a sheet of unpolished glass of ebonite. The figure is 7 centimeters long and 2 centimeters broad. A layer of this kind polished with a burnisher has a very variable resistance. With a little care, one can prepare sheets which are more or less sensitive to electrical action. Metal powders or metal filings are not the only sensitive substances, as powdered galena, which is slightly conducting under pressure, conducts much better after having been submitted to electrical influence. Powdered binoxide of manganese is not very sensitive unless mixed with powdered antimony and compressed. Making use of the A arrangement with very short sparks at S, the figure, the phenomenon of increased conductivity can be observed with platinized and silvered glass, also with glass covered with gold, silver, and aluminium foil. Some of the mixtures employed had the consistency of paste. These were mixtures of colza, oil, and iron, or antimony filings, and of ether or petroleum and aluminium, and plumbago, and other mixtures were solid. If we make a mixture of iron filings and Canada balsam melted in a water bath, and pour the paste into a little ebonite cup, the ends of which are closed by metallic rods, a substance is obtained which solidifies on cooling. The resistance of such a mixture is lowered from several megohms to a few hundred ohms by an electric spark. Similar results are obtained with a solid rod composed of fused flowers of sulfur and iron or aluminium filings, also by a mixture of melted resin and aluminium filings. In the preparation of these solid, sensitive mixtures, care must be taken that the insulating substance should only form a small percentage of the whole. Some interesting results are also obtained with mixtures of sulfur and aluminium, and with resin and aluminium when in a state of powder. When cold, these mixtures, as a rule, do not conduct either directly or after they have been exposed to electrical influences, but they become conducting on combining pressure with electrical influences. Thus, a mixture of flowers of sulfur and aluminium filings in equal volumes was placed in a glass tube 24 millimeters in diameter. The weight of the mixture was 20 grams, and the height of the column 22 millimeters, with a pressure of 186 grams per square centimeter, 2 GIB per square inch. The mixture is not conducting, but after exposure to electrical influence, obtained by the arrangement, the resistance falls to 90 ohms. In a similar manner, a mixture of selenium and aluminium placed in a tube 99 millimeters long was not conducting until after it was exposed to the combined influence of pressure and electricity. The following is one of the group of numerous experiments of a slightly different character. A mixture of flowers of sulfur and fine aluminium filings containing 2 of sulfur to 1 of aluminium is placed in a cylindrical glass tube 35 millimeters long. By means of a piston, a pressure of 20 kilograms per square centimeter, 284 IB per square inch was applied. It was only necessary to connect the column for 10 seconds to the poles of a 25-cell battery for the resistance originally infinite to be reduced to 4,000 ohms. The arrangement shown in the figure illustrates another order of experiment. 2 rods of copper were oxidized in the flame of a Bunsen burner and were then arranged to lie across each other as shown, and were connected to the terminals of the arm of a wheatstone bridge, the high resistance of the circuit being due to the layers of oxide. Amongst the many measurements made, I found in one case a resistance of 80 ohms, which, after exposure to the influence of the electric spark, was reduced to 7 ohms. Analogous effects are obtained with oxidized steel rods. Another pretty experiment is to place a variations of conductivity cylinder of copper with an oxidized hemispherical head on a sheet of oxidized copper. Before exposure to the influence of the electric spark, the oxide offers considerable resistance. The experiment can be repeated several times by merely moving the cylinder from one place to another on the oxidized sheet of copper, thus showing that the phenomenon only takes place at the point of contact of the 2 layers of oxide. It may be worth noting that for most of the substances enumerated, an elevation of temperature diminishes the resistance, but the effect of a rise of temperature is transient and is incomparably less than the effect due to currents of high potential. For a few substances, the 2 effects are opposed, restoration of original resistance. The conductivity caused by the various electrical influences lasts sometimes for a long period, 24 hours or more, but it is always possible to make it rapidly disappear, particularly by a shock. The majority of substances tested showed an increase of resistance on being shaken, previous to being submitted to any special electrical influence. But after having been influenced, the effect of shock is much more marked. The phenomenon is best seen with the metallic filings, but it can also be observed with metallized ebonite sheets with mixtures of liquid insulators and metallic powders. Mixtures of metallic filings and insulating substances, compressed or not compressed. And finally, with solid bodies, I observed the return to original resistance in the following manner. The sensitive substance was placed at K, the figure, and formed part of a circuit which included a Daniell cell and galvanometer. At first, no current passes. Sparks are then caused at ES, and the needle of the galvanometer is permanently deflected. On smartly tapping the table supporting the ebonite cup in which the sensitive substance is contained, the original condition is completely restored. When the electric action has been of a powerful character, violent blows are necessary. I employed for the purpose of these shocks a hammer fixed on the table, the blows of which could be regulated. With some substances, when feebly electrified, the return seemed to be spontaneous, although it was slower than the return of the galvanometer needle to equilibrium. This restoration of the original resistance is attributable to surrounding trepidations, as it was only necessary to walk about the room at a distance of a few meters, or to shake a distant wall. This spontaneous return to original resistance after weak electrical action was visible with a mixture of equal parts of fine selenium and tellurium powders. The restoration of resistance by shock was not observable, so long as the electrical influence was at work. After having been submitted to powerful electric action, shock does not seem to entirely restore substances to their original state. In fact, the substances generally show greater sensitiveness to electric action. Thus, a mixture of colza oil and antimony powder being exposed to the influence of arrangement, a spark of 5 millimeters, was at first necessary to break down the resistance, but after the conductivity had been made to disappear by means of blows, a spark of only 1 millimeters was sufficient to again render the substance conducting. Finely powdered aluminium has an extremely high resistance. A vertical column of powdered aluminium 5 millimeters long of 4 square centimeters cross-section, submitted to considerable pressure, completely stopped the current from a Daniell cell. The influence of arrangement produced no effect, but by direct contact with a Leyden jar, the resistance was reduced to 50 ohms. The effect of shock was then tried, and after this, the sparks produced by arrangement were able to reduce the resistance. The following experiment is also of the same kind. Aluminum filings placed in a parallelepipedic trough completely stopped the current from a Daniell cell, and the resistance offered to a single cell remained infinite after the trough had been placed in the circuit of 25 sulfate of mercury cells for 10 seconds. The aluminium was next placed in circuit with a battery of 75 cells. A single Daniell cell was then able to send a current through the substance. The original resistance was restored by shock, but not the original condition of things, since a single cell was able to send a current after the aluminum had been circuited for 10 seconds with a battery of only 25 cells. I may add that if the restoration of resistance was brought about by a violent shock, it was necessary to place the aluminum in circuit with 75 cells for 1 minute, before the resistance was again broken down. It must be observed that electrical influence is not always necessary to restore conductivity after an apparent return to the original resistance, repeated feeble blows being sometimes successful in bringing this about. Both in the case of slow return by time and sudden return by shock, the original value of the resistance is often increased. Eads of carocarbon, 1 meter long and 1 millimeters in diameter, were particularly noticeable for this phenomenon. Return to original resistance by temperature elevation. A plate of coppered ebonite rendered conducting by electricity and placed close to a gas jet quickly regained its original resistance. A solid rod of resin and aluminium, or of sulfur and aluminium rendered conducting by connection to the poles of a small battery, will regain its original resistance by shock. But if the conducting state has been caused by powerful means, such, for instance, as direct contact with a Leyden jar, shock no longer has any effect, at least such a shock as the fragile nature of the material can stand. A slight rise of temperature, however, has the desired result. By suitably regulating the electric action, it is possible to get a substance into such a condition that the warmth of the fingers suffices to annul conductivity, influence of surrounding. Electric action gives rise to no alteration of resistance when the substance is entirely within a closed metal box. The sensitive substance in circuit with a Daniell cell and a galvanometer is placed inside a brass box, the figure. The absence of current is ascertained, the circuit broken, and the box closed. A Wimshurst machine is then worked a little way off, and will be found to have had no effect. The same result will be obtained if the circuit is kept closed during the time the Wimshurst machine is in operation. Appendix C. If a wire connected at some point to the circuit is passed out through a hole in the box to a distance of 20 to 50 cms, the influence of the Wimshurst machine makes itself felt. On tapping the lid to restore resistance, the galvanometer needle remains deflected so long as the sparks continue to pass. If, however, the wires are pushed in so that they only project a few millimeters, the spark still passing, a few taps suffice to bring back the needle to zero. On touching the end of the wire with the fingers or a piece of metal, conductivity is immediately restored. The movements of the galvanometer needle were rendered visible in these experiments by looking through a piece of wide mesh wire gauze with a telescope. The respective position of the things was reversed. That is to say, a Kumkorf coil and a periodically discharged Leyden jar were placed inside and the sensitive substance outside the box with the same results. In some later experiments with a larger metallic case, and with the Daniell cell, sensitive substance, delicate galvanometer, and Wheatstone bridge placed inside, I found that a double casing was necessary in order to absolutely suppress all effects. A glass covering afforded no protection. Considerations on the mechanism of the effects produced. What conclusions are we to draw from the experiments described? The substances employed in these investigations were not conductors, since the metallic particles composing them were separated from each other in the midst of an insulating medium. It was not surprising that currents of high potential, and especially currents induced by discharges, should spark across the insulating intervals. But as the conductivity persisted afterwards, even for the weakest thermoelectric current, there is some ground for supposing that the insulating medium is transformed by the passage of the current, and that certain actions, such as shock and rise of temperature, bring about a modification of this new state of the insulating body. Actual movement of the metallic particles cannot be imagined in experiments where the particles in a layer a few millimeters thick were fixed in an invariable relative position by extreme pressures, reaching at times to more than 100 kilograms per square centimeter, 1420 IB to the square inch. Moreover, in the case of solid mixtures, in which the same variations of resistance were produced, displacement seems out of the question. To explain the persistence of the conductivity after the cessation of the electrical influence, are we to suppose, in the case of metallic filings, a partial volatilization of the particles creating a conducting medium between the grains of metal? In the case of mixtures of metallic powders and insulating substances agglomerated by fusion, are we to suppose that the thin insulating layers are pierced by the passage of very small sparks, and that the holes left behind are coated with conducting material? If this explication is admissible for induced currents, it must hold good for continuous current. If so, we must conclude that these mechanical actions may be produced by batteries of only 10 to 20 volts electromotive force, and which only cause an insignificant current to pass. The following experiment is worth quoting in this connection. A circuit was formed by a Daniell cell, a sensitive galvanometer, and some aluminium filings in an ebonite cup. The galvanometer needle remained at zero. The filings were cut out of this circuit and switched for 1 minute into circuit with a battery of 43 sulfate of mercury cells. On being replaced in the first circuit, the filings exhibited high conductivity. The result was the same when 10 or 20 cells were employed, or when the current was diminished by interposing in the circuit a column of distilled water 40 centimeters long and 20 millimeters. The cells used had a high internal resistance, thus 43 cells, 60 volts. When short-circuited, only gave a current of 5 milliamperes. The same battery with the column of distilled water in circuit only caused a deflection of 100 millimeters. On a scale 1 meter off with an astatic galvanometer wound with 50 zero turns. We can therefore see how infinitesimally small the initial current must have been when the filings were added to the circuit. The battery acted, therefore, essentially by virtue of its electromotive force. If mechanical displacement of particles or transportation of conducting bodies seem inadmissible, it is probable that there is a modification of the insulator itself. the modification persisting for some time by virtue of a sort of coercive force, an electric current of high potential, which would be completely stopped by a thick insulating sheet, may be supposed to gradually traverse the very thin dielectric layers between the conducting particles, the passage being effected very rapidly if the electric pressure is great, and more slowly if the pressure is less. Increase of resistance. An increase of resistance was observed in these investigations less often than a diminution. Nevertheless, a number of frequently repeated experiments enable me to say that increase of resistance is not exceptional, and that the conditions under which it takes place are well defined. Short columns of antimony or aluminum powder, when subjected to a pressure of about 1 kilogram per square centimeter per square inch, and offering but a low resistance, exhibited an increase of resistance under the influence of a powerful electrification. Peroxide of lead, a fairly good conductor, always exhibited an increase. So also did some kinds of platinized glass, while others showed alternate effects. For instance, a sheet of platinized glass, which offered a resistance of 700 ohms, became highly conducting after 150 sulfate of mercury cells had been applied to it for 10 seconds. This condition of conductivity was annulled by contact with a charged Leyden jar and reappeared after again applying 150 cells for 10 seconds and so on. Similar effects were obtained with a thin layer of a mixture of selenium and tellurium poured when fused into a groove in a sheet of mica placed between 2 copper plates. These alternations were always observed several times in succession and at intervals of several days. These augmentations and alternations are in no way incompatible with the hypothesis of a physical modification of the insulator by electrical influence. Chapter 28. Appendix D Researches of Prof. D. Hughes waves and their application to W. Wireless telegraphy, 1879 to 1886. It may be desirable to place briefly on record the circumstances under which the following remarkable communication was written. While revising the last sheets of this work, it occurred to the author to ask Sir William Crookes for some particulars of the experiments, to which he alluded in his fortnightly article, some passages from which are quoted on 199 on April 22nd. 1899, Sir William replied as follows: Dear Mr. Fahie, the experiments referred to at page 176 of my fortnightly article as having taken place some years ago were tried by Professor Hughes when experimenting with the microphone. I have not ceased since then urging on him to publish an account of his experiments. I do not feel justified in saying more about them, but if you were to write to him telling him what I say, it might induce him to publish. It is a pity that a man who was so far ahead of all other workers in the field of wireless telegraphy should lose all the credit due to his great ingenuity and provision. Believe me, very truly yours, William Crookes. On receipt of this letter, I wrote to Professor Hughes. In reply, he said, Your letter of 26th instant has brought upon me a flood of old souvenirs in relation to my past experiments on aerial telegraphy. They were completely unknown to the general public, and I feared that the few distinguished men who saw them had forgotten them, or at least had forgotten how the results shown them were produced. At this late date, I do not wish to set up any claim to priority, as I have never published a word on the subject. And it would be unfair to later workers in the same field to spring an unforeseen claimant to the experiments which they have certainly made without any knowledge of my work. On second, and my readers will say, wiser thoughts. Professor Hughes sent me the following letter, in the eliciting of which I consider myself especially fortunate and privileged. Dear Sir, in reply to yours of the 26th inst., in which you say that Sir William Crookes has told you that he saw some experiments of mine on aerial telegraphy in about December 1879, of which he thinks I ought to have published an account, and of which you ask for some information. I beg to reply with a few leading experiments that I made on this subject from 1879 up to 1886. In 1879, being engaged upon experiments with my microphone, together with my induction balance, I remarked that sometimes I could not get a perfect balance in the induction balance, through apparent want of insulation in the coils. But investigation showed me that the real cause was some loose contact or microphonic joint excited in some portion of the circuit. I then applied the microphone and found that it gave a current or sound in the telephone receiver. No matter if the microphone was placed direct in the circuit or placed independently at several feet distance from the coils through which an intermittent current was passing. After numerous experiments, I found that the effect was entirely caused by the extra current produced in the primary coil of the induction balance. Further research has proved that an interrupted current in any coil gave out at each interruption such intense extra currents that the whole atmosphere in the room, or in several rooms distant, would have a momentary invisible charge, which became evident if a microphonic joint was used as a receiver with a telephone. This led me to experiment upon the best form of a receiver for these invisible electric waves, which evidently permeated great distances and through all apparent obstacles, such as walls and seat. I found that all microphonic contacts or joints were extremely sensitive. Those formed of a hard carbon, such as coke or a combination of a piece of coke resting upon a bright steel contact, were very sensitive and self-restoring, whilst a loose contact between metals was equally sensitive, but would cohere or remain in full contact after the passage of an electric wave. The sensitiveness of these microphonic contacts in metals has since been rediscovered by Mons Branly of Paris and by Professor Oliver Lodge in England, by whom the name of coherer has been given to this organ of reception. But as we wish this organ to make a momentary contact and not cohere permanently, the name seems to me ill-suited for the instrument. The most sensitive and perfect receiver that I have yet made does not cohere permanently, but recovers its original state instantly, and therefore requires no tapping or mechanical aid to the separation of the contacts after momentarily being brought into close union. I soon found that, whilst an invisible spark would produce a thermoelectric current in the microphonic contacts, sufficient to be heard in the telephone in its circuit, it was far better and more powerful to use a feeble voltaic cell in the receiving circuit. The microphonic joint then acting as a relay by diminishing the resistance at the contact under the influence of the electric wave received through the atmosphere. I will not describe the numerous forms of the transmitter and receiver that I made in 1879, all of which I wrote down in several volumes of manuscripts in 1879, but these have never been published, and most of which can be seen here at my residence at any time. But I will confine myself now to a few salient points. I found that very sudden electric impulses, whether given out to the atmosphere through the extra current from a coil or from a frictional electric machine, equally affected the microphonic joint, the effect depending more on the sudden high potential effect than on any prolonged action. Thus, a spark obtained by rubbing a piece of sealing wax was equally effective as a discharge from a Leyden jar of the same potential. The rubbed sealing wax and charged Leyden jar had no effect until they were discharged by a spark. And it was evident that this spark, however feeble, acted upon the whole surrounding atmosphere in the form of waves or invisible rays, the laws of which I could not at the time determine. Hertz, however, by a series of original and masterly experiments, proved in 1887 to 89 that they were real waves similar to light, but of a lower frequency, though of the same velocity. Whilst making these experiments on aerial transmission, I had two different problems to solve. First, what was the true nature of these electrical aerial waves, which seemed, whilst not visible, to spurn all idea of insulation, and to penetrate all space to a distance undetermined. Second, to discover the best receiver that could act upon a telephone or telegraph instrument so as to be able to utilize, when required, these waves for the transmission of messages. The second problem came easy to me when I found that the microphone, which I had previously discovered in 1877 to 78, had alone the power of rendering these invisible waves evident, either in a telephone or a galvanometer, and up to the present time, I do not know of anything approaching the sensitiveness of a microphonic joint as a receiver. Branly's tube, now used by Marconi, was described in my first paper to the Royal Society in May 1878 as the microphone tube, filled with loose filings of zinc and silver, and Professor Lodge's coherer is an ordinary steel microphone, used for a different purpose from that in which I first described it. During the long-continued experiments on this subject between 1879 and 1886, many curious phenomena came out which would be too long to describe. I found that the effect of the extra current in a coil was not increased by having an iron core as an electromagnet. The extra current was less rapid and therefore less effective. A similar effect of a delay was produced by Leyden jar discharges. The material of the contact breaker of the primary current had also a great effect. Thus, if the current was broken between two or one piece of carbon, no effect could be perceived of aerial waves, even at short distances of a few feet. The extra current from a small coil without iron was as powerful as an intense spark from a secondary coil, and at that time, my experiment seemed to be confined to the use of a single coil of my induction balance, charged by 6 Daniell cells. With higher battery power, the extra current invariably destroyed the insulation of the coils. In December 1879, I invited several persons to see the results then obtained. Amongst others who called on me and saw my results were, at 1879, Mr. W.H. Preece F.E.S., Sir William Crookes F.R., Sir W. Roberts, Austin F.R.s, Professor W. Grills Adams, F.R.s, Mr. W. Grill Febby. 1880, Mr. Spottiswoode Press R.S., Professor Huxley F.R., Sir George Gabriel Stokes, F.R.S. Novice 7, 1888. Professor Dewar F.R.S. Mr. Lennox. They all saw experiments upon aerial transmission, as already described, by means of the extra current produced from a small coil and received upon a semi-metallic microphone. The results being heard upon a telephone in connection with the receiving microphone. The transmitter and receiver were in different rooms, about 60 feet apart. After trying successfully all distances allowed in my residence in Portland Street, my usual method was to put the transmitter in operation and walk up and down Great Portland Street with the receiver in my hand, with the telephone to the ear. The sound seemed to slightly increase for a distance of 60 yards, then gradually diminish, until at 500 yards I could no longer with certainty hear the transmitted signals. What struck me as remarkable was that, opposite certain houses, I could hear better, whilst at others, the signals could hardly be perceived. Hertz's discovery of nodal points in reflected waves has explained to me what was then considered a mystery. At Mr. A. Stroh's telegraph instrument manufactory, Mr. Stroh and myself could hear perfectly the currents transmitted from the 3rd story to the basement, but I could not detect clear signals at my residence about a mile distant. The innumerable gas and water pipes intervening seemed to absorb or weaken too much the feeble transmitted extra currents from a small coil. The president of the Oil Society, Mr. Spottiswoode, together with the 2 honorable secretaries, Professor Huxley and Professor G. Stokes, called upon me on February 20th, 1880, to see my experiments upon aerial transmission of signals. The experiments shown were most successful, and at first they seemed astonished at the results. But towards the close of 3 hours' experiments, Professor Stokes said that all the results could be explained by known electromagnetic induction effects, and therefore he could not accept my view of actual aerial electric waves unknown up to that time, but thought I had quite enough original matter to form a paper on the subject to be read at the Oil Society. I was so discouraged at being unable to convince them of the truth of these aerial electric waves that I actually refused to write a paper on the subject until I was better prepared to demonstrate the existence of these waves. And I continued my experiments for some years in hopes of arriving at a perfect scientific demonstration of the existence of aerial electric waves produced by a spark from the extra currents in coils, or from frictional electricity, or from secondary coils. The triumphant demonstration of these waves was reserved to Professor Hertz, who by his masterly researches upon the subject in 1887 to 89 completely demonstrated not only their existence, but their identity with ordinary light in having the power of being reflected and refracted, and see, with nodal points by means of which the length of the waves could be measured. Hertz's experiments were far more conclusive than mine, although he used a much less effective receiver than the microphone or coherer. I then felt it was now too late to bring forward my previous experiments, and through not publishing my results and means employed, I have been forced to see others remake the discoveries I had previously made as to the sensitiveness of the microphonic contact and its useful employment as a receiver for electric aerial waves. Amongst the earliest workers in the field of aerial transmission, I would draw attention to the experiments of Professor Henry, who describes in his work published by the Smithsonian Institute, Washington, B.C., USA, followed day unknown, probably about 1850, how he magnetized a needle in a coil at 30 feet distance and magnetized a needle by a discharge of lightning at 8 miles distance. Marconi has lately demonstrated that by the use of the Hertzian waves and Branly's coherer, he has been enabled to transmit and receive aerial electric waves to a greater distance than previously ever dreamed of by the numerous discoverers and inventors who have worked silently in this field. His efforts at demonstration merit the success he has received. And if, as I have lately read, he has discovered the means of concentrating these waves on a single desired point without diminishing their power, then the world will be right in placing his name on the highest pinnacle in relation to aerial electric telegraphy. Sincerely yours, D. Hughes, J.J. Fahie, Esquire, Claremont Hill, St. Helens, Jersey. In the 50 years just completed of a brilliant professorial career at Cambridge, Sir George Stokes has given, times out of number, sound advice and helpful suggestions to those who have sought him. But in this case, as events show, the great weight of his opinion has kept back the clock for many years. With proper encouragement in 1879 to 80, Professor Hughes would have followed up his clues, and with his extraordinary keenness in research, there can be no doubt that he would have anticipated Hertz in the complete discovery of electric waves, and Marconi in the application of them to wireless telegraphy, and so have altered considerably the course of scientific history. As a recent commentator pithily says, Hughes's experiments of 1879 were virtually a discovery of Hertzian waves before Hertz, of the coherer before Branly, and of wireless telegraphy before Marconi and others. The writer goes on to say, Professor Hughes has a great reputation already, but these latter experiments will add enormously to it, and place him among the foremost electricians of all time, praise which, knowing the learned professor as I do, I consider none too great.